What is Kafka? What are the different options through which we can do asynchronous processing? Now, what is a message queue? Now, what is event streaming? What is the difference between message queue and event streaming? Another question may come into your mind is, in which category does Kafka lie? Is Kafka a message queue or event stream? Is Kafka message queue or event stream? Why I am doing that? Because for a long while, I just assumed that Kafka lies in the category of message queue. Okay, but when I learned about the complete topic, it was like, wow, oh, I was like thinking totally wrong. Now, what is a topic? Is topic same as event? We said like in Kafka we will have the events, but question would be, where are these events stored? What is a broker? What is a partition? Why do we have multiple brokers in Kafka? Where do we store data inside this broker? Is it inside the topic? Now you would say, why do we have partition if we already have the topic? Right? Can a broker contain multiple partitions? Can a broker contain events of different topics? What about the partition? What if this P0 fails? How can we avoid single point of failure here? How about the ordering of events? What is a consumer group? Are topic and event the same? What is the relation between a topic and partition? How do we add a new topic? And who adds it? Now, what is an offset? Where are offsets stored? And who stores the offset? How do consumers consume events from Kafka? Like, is it the observer pattern that the events get pushed to the consumers by Kafka, or how does that work? What if wrong data goes into Kafka? We said like follower will replicate from the leader, correct? But here we know that follower is some other broker and leader is some other broker. So how is follower replicating the data from the leader? How many replicas do we usually keep for partitions? How does Kafka metadata look like? What is the complete end-to-end Kafka flow? Why is ordering guaranteed in a partition but not across the partitions? Can multiple consumers read from the same partition at the same time? As we discussed earlier, that you need to provide the number of partitions while defining the topic. So the question is, how many partitions should we choose at the beginning? Which is, as we have defined the partitions in the beginning, what if events become huge later? Can we increase the partitions? When are events deleted from Kafka? What are the different offset commit strategies in Kafka? And what are the different delivery guarantees, like at most once, at least once, or exactly once in Kafka? And which one of these is the default one in Kafka? What happens during consumer crash? Does every event have an offset? And who assigns the offset? What is backpressure? What happens internally when a topic is created? How to add a consumer group to existing topic? Why is Kafka so good at handling massive writes? Or how does Kafka handle huge number of writes? How does Kafka handle so many read operations? What is the difference between PubSub and Kafka? Why Kafka is not just PubSub? When to use Kafka and when to use PubSub? What is the difference between Kafka and RabbitMQ? Is Kafka message queue or event stream? Can a partition contain event of multiple topics? We saw like a topic can contain multiple partitions, right? But can a partition contain events of different topics? Do we create new partitions for every new topic? Can a consumer in consumer group consume from multiple topics? Can a consumer in a consumer group consume from multiple partitions of the same topic? So now we are thinking in terms of same topic. I got a lot of comments on my YouTube channel to make a video on Kafka. So today we are going to talk about Kafka. See, I'm listening to you. So what I want from you is to make sure you like this video, subscribe to the channel and share it with your friends and family so that I can create more such wonderful content for you. Honestly, I tried to search a video on Kafka so that I can learn from it, but I wasn't able to find a good video related to that. So I thought I'll create a video from which you will be able to understand Kafka from very beginner level to the advanced level. Okay, so make sure you watch this video till the end and you will get great clarity about Kafka. Alright, let's start with the video. Now before we talk about Kafka, let's start with the problem statement. Imagine we have a system like Amazon, okay, and now user has placed an order on Amazon. Then after that, a lot of things needs to be done, like we need to save the order in database, we need to reduce the inventory count, correct? Say for example, earlier for a particular item, there were like 30 units were available. once user has placed an order for one of the items, so you have to reduce the count from 30 to 29, right? So you have to update your inventory count because this represents the count of inventory which is left in your system, right? Now, apart from that, you also need to send the confirmation email to the user. You need to send SMS. Your system needs to notify the warehouse. You need to generate the invoice, and you also need to update analytics. Apart from these as well, depending on your system, you may need to do much more things, right? So you can clearly see when a user places an order, there are a lot of things that needs to be done in the system. Now the question comes, how will we perform all these steps? Now a brute force level approach that may come into your mind would be, we would do things synchronously. Like when user places an order, it goes to the order service, and then from that we'll go to the inventory microservice, and then to the email microservice, then to SMS microservice, and then to the analytics microservice. Okay, so we are performing all of these things synchronously. When I say synchronously, it means like the API request will wait for all of the steps to be completed, and once all of the steps are completed, we will send the response through API. Okay, but if we do it synchronously, there can be a lot of problems. Let's check those out. Now the first problem is user will have to wait until all of these finish, right? Because we have said we are doing it synchronously, which means after this we will do this, after this we will do this, and then this, and then this, and we will not send back the response till all of these are finished, right? So the user will keep on waiting till we have finished all of these, correct? So overall you can imagine there will be a huge amount of latency. It will be a very slow response, and it can be a really bad user experience because user is just waiting for things to happen, because user doesn't know like you have to do all of these things. For user it's a simple system. User has placed the order, user should get like your order is successful, right? User doesn't care about all of these steps that you want to do on your backend system, correct? But because we are doing all of these synchronously, so user has to wait for it. So user will keep on seeing that loading icon, which is a very bad user experience. Next problem is that if any of the microservice is slow here, the overall response will become slow, correct? Because we are sending the response only when all of these are completed. So if any of these microservice is responding slowly, then your overall API response will be slow and the end user will be impacted by it. Another problem is that if any of the service is down or not working, your order will simply fail because all of these are kind of dependent, and you are sending the response only when all of these pass. So if any of the microservice is not working here, user will not be able to place the order, which is drastic user experience, right? So bad, and it's a really fragile system. So basically we saw a technical example here. Let me also tell you a real life kind of example through which you may get more clarity about it. Okay, so say for example you want to order some food, and this is a place where you can place your order. Now there is a queue right here, and once you reach to this point, you can place your order. Right now, say you make a request to get a pizza. Okay, so just imagine now if you have placed your order, you cannot leave this place because your food is getting prepared, and if you leave this place, then there is a huge amount of queue. Again, you have to be part of the queue. This is a really bad experience because the customer is blocked now. Customer cannot go anywhere else. Customer has to stand in the queue waiting for the food, right? So this is same example as this one which we mentioned, right? So clearly you can see it's the chef who is preparing the food. This customer is not related to that work, correct? But still customer needs to wait because the food is not ready right now. And if the customer leaves the queue, then again customer needs to be part of the huge queue out there, right? So same here, you can see user has already placed the order, but because we need to do some of the additional work like here preparing of food, or here you can say inventory service, email service, and much more, although these are not directly related to the end user, but still user has to wait for it. So this is the synchronous way, and this is also the synchronous way, and it doesn't make any sense. How do we solve this kind of problem? It's simple. Like when you reach to the counter, you place an order, like you say I want pizza, so they will take your order, and what they will do is like they will provide you a token or some order ID, like your order number is 32. Okay, and there is a display out there which says like order number 32 ready, right? Or there can be other options that once the order is ready, they can drop you a text or they can call you. So what happens is like once you get the order number, you can leave that place, right? You can do whatever you want to do. You can leave that queue, you can go sit and watch the television, you can talk to your friends, you can go outside, because once your order is ready they'll call you. So it's kind of, you are not blocked here, right? So this way is asynchronous processing, right? Whereas this way was synchronous processing. Like you were blocked here, even though the things which were happening were not directly related to you, still you were blocked. But here, once you place the order, you got some order ID or order number or any token you can say, and you are free to do whatever you want to do. You are not blocked here, correct? In similar terms, what we want here is when user has placed the order, we have done the processing on order microservice, user should get some response here like this was successful, okay? And rest of the things can happen asynchronously so that the end user is not blocked, correct? So this was a real life example and this was a technical example. Now let me give you one more technical example so that you get more clarity. Okay. So when we talk about YouTube and say a user is uploading the video on YouTube. Okay. So this is the end user, or you can say the client, and this is the server. Okay. So you are uploading the video on the YouTube, right? So what happens is like, apart from uploading the raw video on YouTube, there are a lot of many other steps that happen. So if you want to know more about like how to design a system like YouTube, you can refer to this video of mine. I've talked in detail in this, but just to give you summary here, a lot of things are involved. Like you need to transcode the video into different resolutions. Like you can have 720p, you can have 480p, you can also have like 1080 or 4K or 144p, all those resolutions. So you need to do all those transcoding. Apart from that, you also need to do the copyright checks. Okay, then you also need to generate the automatic thumbnails, right? And you also need to do the analytics, and there are much more steps that you want to do whenever a video is uploaded, correct? So the synchronous way of doing things would be, user has uploaded the video and you will do all of these one by one, and till the time you have not completed all of these things, user will not get the success, correct? So the API response will be dependent on all of these microservices, and of course the end user experience will be very bad, because if any of these steps fails, user will get the failure. So user will not be able to upload the video. And you can imagine, because we are doing so many things out there, user has to wait for so much time, user will be blocked on that part. So this is synchronous way of doing things, but it is a very bad experience for the end user. So instead of doing this way, what we want is asynchronous processing. So we have mentioned here, what we want is asynchronous processing. So in that, what will happen is like, once the user has uploaded the raw video, user will get success as a response on that API request, and then rest of the steps can be done asynchronously. Okay, so that overall user experience is good. Now we have mentioned we should do it asynchronously rather than doing it synchronously, but the question comes, how can we do it asynchronously? Of course, because we are talking about Kafka, so Kafka is one of the options, right? But let's see what all are the options which are present through which we can solve this problem, or through which we can perform this task asynchronously. All right, so this is the part that we want to discuss now. Of course, the question is like, what are the different options through which we can do asynchronous processing? Okay, the first option is background jobs using the application threads. So what we can do is like, we can create a background thread or the executor inside the same service. So basically we will have a task and the background thread will pick the task and perform it. Because we are doing this using a background thread, this is asynchronous processing. So if you want to know more about like background threads and multi-threading, you can refer to this video of mine, through which you will get more clarity. But because here we are discussing more in terms of system design, this is not that important. Okay, why? Let me show you the pros and cons through which you will understand why I'm saying that. Okay, first of all, you can use this using this way. You can see we are using an executor here. We have written executor.submit, and it's a lambda function. Inside that we have performed whatever action we want to perform. right? So using the background thread or executor is our first way. Talking about the pros, this is very simple. Of course, you can see here quite simple piece of code. No infra is required for this. We have low latency and this is good for small applications. Okay, now because we mentioned that the executor is part of the same service, so if by any chance this service crashes, your job will be lost, right? Another con is that there are no retries, there is no durability. Why no durability? This is related to the first point that we discussed, because the executor is part of the same service. Okay, it's not like this executor is kind of a distributed system, right? It is part of one particular service, and if service goes down, that job is lost, and hence there is no durability here. And a big con here is it is not scalable across machines. Why? Because we are talking about the executor inside the same service or machine. Okay, now when to use this approach? When you have single server application, you have non-critical task in your side projects or POCs. Okay, but the main point is when we talk about like system design, here I'm talking about like high level design, right? So we always think in terms of distributed systems. We have multiple servers, we have multiple machines. So that's why I said, like, when we think in terms of system design, this approach doesn't make much sense. This makes sense when you talk about like single server application or small projects or POCs, or this is more about like low level design when you are executing in the same service. All those things can come into picture. But when we think in terms of like high level design, distributed systems, many machines, many services, then this approach doesn't make much sense, because this is unreliable, this is not durable, this is not fault tolerant. All right, so after this, let's see the second option, which is using the database, right? We know about database, and if you're not sure about database, refer to this video. In this 8 to 9 hours video, I've discussed in detail about database. Watch this video and you'll get complete clarity about all the databases. Okay, so go check that out. But one option that for sure comes into mind is like we can use database, right? Something like we can put the things in the database and then we can keep on polling that from the database and then use that asynchronously, right? So like from the order service, we put this in the database and say we have this task table, right? And then there are different workers. Those will simply poll the database, and once they poll the task, they can process the task asynchronously. Now what are the pros to this approach? This is durable because DB has persistent storage, correct? The earlier case that we discussed, this was not persistent, correct? There was no durability because the executor was part of some service, and if the service goes down, the job was lost. So this was not durable, this was not persistent storage. But when we talk about the database, we have like persistent storage, and hence this is durable. Another good part is that it is easy to implement and we have simple retry logic. Now when we talk about the cons, polling the database is inefficient. Okay, so you will keep on polling the database, so that is not a good thing. And simply you can see there are a lot of workers or consumers which will keep on reading the data from the database. In this way, you are increasing the load on the database. First you are putting a lot of write operations here and then a lot of read operations here. So we are putting huge amount of load on the database, and database can go down, right? So that is a really bad thing. Another issue here is that scaling the workers is painful and ordering is hard. Okay, so yeah, database comes as a very simple option into mind. Okay, yeah, we can use the database, but it's not a great option, because simply you can think in this way, you are putting a lot of write operations and read operations, and putting that much load on the database, it's not good for your system. So this approach is not scalable when we talk about like high throughput, and hence we don't use this approach when there is high throughput. Okay, the third option is using the cron jobs or scheduled workers. So it means that you have some job or worker which run at fixed intervals. Like for example, it runs after every 5 minutes or after every 1 hour, depending on what type of task it is. You can set it at fixed intervals. Some of the examples can be send reminder emails, clean up old data, and to generate the daily reports. Now let's see some of the pros and cons for this strategy. Talking about the good part, it is extremely simple. It has predictable execution and there is no event dependency. And talking about the cons, it is not real time. Why? Because the job runs at fixed intervals. So say earlier it ran at around 8 p.m. and next it will run at 9 p.m. Okay, now if anything happens in between this time like 8:25, it has to wait for the next interval to come, hence it is not real time. And due to this, another con is there can be some delay, and hence it is not a great option when we talk about user triggered actions, right? It is okay if we talk about generating daily reports or sending reminder emails, but if we talk about the requirements which are real time or user related important tasks, then it is not great for that. So now let's see when to use cron jobs or scheduled workers. You can use it when we have time based async work. Of course, we are talking about the options for asynchronous work, but here you can use it when your async work is time based and when you can do batch processing. Why batch processing? Because your job is running at fixed intervals and all the things which happened in between the last time the job ran and the new time when the job is running, all of those can be processed in a batch, and it can be also used for maintenance tasks. So basically the cron jobs or the scheduled workers, these are time driven and not event driven. Don't worry about event because we will discuss about events in detail later in this video. But in short, if I have to tell you, like, it is not like if some particular thing happened, like video uploaded in case of YouTube, and then we have to perform a lot of things like creating the thumbnail, then creating the transcoding for different resolution. All of those things, those can't wait for so much time, and what we want is like whenever that event comes, we want to perform all those things, right? But here this cron job or scheduled workers, this is time driven. So you might see it when we have to do some task which is time driven, some of the examples that we discussed like this. But overall, when we have to perform things asynchronously, when something happens, we can't use this, right? So let's move to the next option. Next option for asynchronous processing is using the webhooks. Now what is a webhook? Basically your system will call someone else endpoint asynchronously. So basically you can think of it as like there is some external system or third party integration and they provide you an endpoint, and basically you will make a request and wait for the callback from that external endpoint. So one of the examples where we use webhooks is while designing the payment system. In that you may use third party or external system through which you'll make the payment, like the Razorpay or Stripe. Okay, so you will make the payment through that platform, but your system will keep on checking with that third party system for particular transaction. So you will call the endpoint of that third party platform and you'll wait for the callback from that external system. So in that we use webhooks. If it sounds confusing for you, don't worry about it, because in this video we are not going to talk in detail about webhooks. But if you want me to talk more on webhooks, put that in comment section and I can create a separate video related to designing the payment system, and in that we can discuss more about the webhooks. Okay, now talking about some of the pros and cons for using the webhooks as asynchronous processing. So first, when we talk about the pros, this is simple. It doesn't require any extra infra and it is good for integrations. Talking about the cons, there can be network failures. Basically, if you see here, there is an endpoint which has been provided by some external or third party system, but we will make the network calls to that endpoint and we will wait for the callbacks, right? So it is happening through the network and there can be network failures. And now, as we said, there can be failures. So retry complexity comes into picture as well, and there can be tight coupling as well. Okay, so webhooks is another option through which we can do asynchronous processing, but this is not what we are looking for in this video. Now talking about when to use the webhooks, we can use it for third party integrations, like I mentioned you, for the payment gateways like the Stripe, Razorpay, or some other systems you can imagine like GitHub style events, right? So overall, webhooks are async but not reliable without retries. Okay, and in this video we are going to discuss more about Kafka, and Kafka doesn't lie into this category. So let's move to the next case. Okay, the next option is serverless or task services. Now before we discuss this, one thing is that you don't need to remember all of these. I'm just telling you so that you get some clarity like how Kafka comes into picture, right? We understood that the problem statement is we want to process thing asynchronously. Okay, so before we talk about Kafka, I want to show you all the different options which are present through which you can do asynchronous processing. We are also checking the pros and cons and when to use which one. And when we discuss all of these, I'll tell you in which category Kafka lies in, and through that you'll get better understanding. Okay, so don't worry to memorize everything, just try to understand the basic concepts, like okay, there are multiple options through which we can do the asynchronous processing, and that gives you more clarity about the overall picture. Okay, so this category of serverless or task services, if you're working in backend, so you might have used like AWS Lambda or Cloud Task or the Azure functions. So these are also used for async execution. If you're new to it, don't worry, just listen through it. It's totally okay if you don't understand this. We won't take much time in this part. We'll move to the next one. I'll just talk about the pros and cons in this. Okay, some of the pros are, first is auto scaling, because we are talking about the cloud. Okay, next is no server management and pay per use. Overall, all of these represent like cloud computing, you can say. So let me explain with a very simple example. Say you have this product, you have the backend for it and you have the front end for it, like you have the website or application, right? So on daily basis you have some particular load, you can say X is the estimate that you get on average, right? But now it's festival season and say your product is related to shopping, or you have put some sale on your products, right? So what can happen is like huge amount of load can come, which can be much more than the average load that comes, right? So one way to handle would be like every time you see there can be a spike, you increase the number of servers so that the load can be managed, correct? Because let's say you had 3 servers, okay, and they were fine to handle X amount of load, but now just imagine huge amount of load comes, and what can happen is like your servers can go down because they won't be able to handle that much load. So the first strategy, as we said, you can increase the number of servers before the sale, right? And after the sale you can decrease it. So this looks fine when we talk about some of the events that you know are going to happen, right? Like because it's a sale time, you know that load might increase, and based on that you can do this management. But sometimes all of a sudden also the load can increase, right? So instead of managing by yourself, there is a feature which is auto scaling, which is provided by the cloud services. So based on the load, they will do it automatically and you don't need to do the particular server management by yourself. Okay, so this is quite good for both cases, when the load increases and decreases, right? And what you need to do is like you have to just pay per the usage. So depending on how much load came and how much was the usage, you just pay based on that part, right? It is basically cloud computing, you can say, through which you can do asynchronous processing. So overall this is part of the cloud computing, you can say. Some of the cons are there can be cold starts, vendor lock-in and execution limits. Now when to use this? For the cloud native systems, okay? But again, if you're new to this, you don't need to remember, okay? So till now we have discussed 5 different options through which we can do the asynchronous processing. Now there are 2 more ways, and which are really interesting and important for this video, because through these we are going to relate to Kafka. Okay, all right. The 6th option is the message queue. Now what is a message queue? So you might have heard or worked on producer consumer problem, right? So let's try to understand in that way. So here comes the producer. Producer represents any component that produces the task, which provides you the task that this needs to be done, okay? And on other side we have the consumer. Consumer is the component which will basically consume and perform that task, right? So producer is saying do this task and consumer will basically perform that task. Now one point to remember here is we are talking about asynchronous processing, which means it's not like whenever producer is asking for any task, consumer will pick at that time, because if we do that way, then it is synchronous processing. The response will have to wait, right? All the problems that we saw, but we want to do the asynchronous processing, and for that message queue comes into picture. Okay, so we have message queue in between, which acts as the temporary storage. Okay, so let me write here message queue. So whatever is the task that can be added in the message queue, and the consumer will consume from the message queue. Okay, so using the message queue we are able to do the asynchronous processing, because the task whatever we want to perform can remain in message queue for some time. So this is acting as the temporary storage. It's not a permanent storage. The task which we kept in the message queue, which was given by the producer, will stay in message queue till the time it is not consumed by the consumer. Once the task has been consumed by the consumer has performed it, that will be removed from the message queue. So it's not a permanent storage, it's a temporary storage, and it is present there just for asynchronous processing, because consumer cannot perform whatever task producer wants to perform at that time. Okay, we want to do that asynchronously, and for that we have the message queue. Now we will discuss more about message queue in detail, but before that let me tell you the seventh option, which is very important. Okay, and after that we will compare things. Now the seventh option is using the event streaming. Okay, in this PubSub is also part of it. We'll discuss more about like PubSub because it is quite famous. Don't worry about it for now. Okay, we'll discuss in detail about message queue, event streaming, Kafka, PubSub, everything in this video. Right now, what is event streaming? As the name suggests, it is based on events. So events are published and there are many consumers which will consume those events. Now you will say we were doing similar thing in message queue. So how is event streaming different from message queue? Don't worry about it. We'll discuss about that in detail. Okay. But before that, as I have told you, 7 different options of asynchronous processing in the table format, let me compare those so that you get bit clarity, and then we'll talk about message queue versus event streaming in detail. Okay. All right, here we go. Here are the 7 different options that we discussed. Okay, and we will see the differences in terms of reliable, scalable and real time. Okay, first, when we talk about in-memory threads, those are not reliable. Why? Because that is part of one system or machine or server, you can say. Once your machine is down, that job will also be lost, right? Also, it's not scalable because here we are talking about this is part of particular machine and we are not talking about the distributed system here, so it's not scalable. Is it real time? Yeah, so you have the background thread that can simply perform the task at that time, so this is real time. Next option that we discussed was database polling. You will put the data or task in the database and then consumers can poll from the database. Right, talking about reliability, this is reliable because database is persistent storage. Talking about scalability, this is not scalable. Why? Because you are putting a lot of load on the database. You are doing a lot of poll operations. So you can imagine there are a lot of write operations because you are entering data in the database, and then there are huge amount of read operations because you are polling from database as well. So it is not scalable when we talk about big systems. Okay, talking about real time, it depends. Basically, if you are polling after some time from the database, then it might not be that real time, but yeah, it depends on your polling frequency. Now the third option that we discussed was the cron jobs. Are these reliable? Yes, these are reliable. After every fixed interval this will run, and whatever happened during that interval, that will be covered by the cron job or the worker. Basically, cron jobs are there to perform time-based work. So you can asynchronously do some of the tasks, but not related to scale on user related things, right? And it is also not real time because as we discussed earlier, so it will happen at fixed intervals. So if something happened in between that interval, that won't be real time, right? That will be fetched when the next interval comes. Now coming to the message queue and event streaming, both message queue and event streaming, these are reliable because as we saw in message queue, the task will be stored in the message queue, although that will be on temporary basis, but that will stay in message queue till the time the consumer has not consumed it, so it is reliable. Similarly, for event streaming, we basically keep those events. Okay, so basically in event streaming, what actually happens is like here you would have the producer, correct, and then we have the Kafka acting as the event stream here. So the events which are produced by the producer will be stored in Kafka, and then there can be multiple consumers. Okay, so there can be multiple consumers which will consume from Kafka. So here, let me put an arrow. All of these will basically consume from the Kafka. So consumers are consuming from Kafka and we are storing the events in the Kafka, right? So hence event streaming is reliable. We'll discuss more about event streaming, don't worry. But yeah, for now, event streaming is reliable. Talking about the scalability, event streaming is like amazing in terms of scalability. So that's why we use Kafka while designing a lot of systems. How is it scalable? We'll discuss about it, don't worry. And both message queue and event streaming are real time as well. Okay, so here I discussed like all of the different various options which are present for asynchronous processing. But for this video, the most important ones are message queue and event streaming. Okay, so you might have a lot of questions about message queue and event streaming. So first, let's see the difference between message queue and event streaming, through which you'll get some more clarity. Okay, so the important question comes, what is the difference between message queue and event streaming? Another question may come into your mind is, in which category does Kafka lie? Is Kafka a message queue or event stream? So let's try to understand that. Basically, the one difference is like you store the task in the message queue. So message queue acts as a task queue. Basically, you tell what task needs to be performed. Okay, and you keep that task in the message queue, then the consumer will pick that task from the message queue. But when we talk about event streaming, we store the events here. We don't store the task here, we store the events. I'll show you examples through which you'll get more clarity. So first, let's see about the message queue. So as I said, we'll store the task in the message queue. So you can also think of it as task queue. Okay, so like a to-do list where you put the task which needs to be performed, right? So each message in the message queue will be a job or a task which needs to be performed. And another important point is we need to process that task once. And once we have performed that task, we just need to forget it. So for example, one of the tasks, you have to send an email. Okay, so once that email is sent, that task from the message queue will be removed because you had to process it once. And once it is performed or processed, you need to remove that from the message queue. So an example, as we said, like sending the email for particular order ID. Now when we talk about event stream, we don't put the task, we put the events, because event stream acts as a log file, you can say a document, a log file where you are just putting the data, and in order to make it like scalable and fast, what we do is like we just append at the end of the file. Okay, so that's why we want things which are immutable. If you put some states in the event stream, then those states are generally mutable. Those keeps on changing, like the state of your order. It can be in the order made state, then it can be in the shipped state, then it can be in the delivered state, then returned state, any of those, right? So the state keeps on changing. But here in event stream, we want to keep the data which is acting as a immutable log or history, okay, which doesn't require much of update. We are just appending at the end of the log file, you can just imagine like that. So that's why it's based more on events, like whatever event happened. Okay, so each event is a fact, which means we are not going to update that event. It was just event and we are processing it. Okay, we are not going to update that event. We will just keep on appending different events which are happening. So the important point to notice, it never changes because we want to make immutable log history file. Why we are doing that or saying that, we'll discuss more about it when we discuss more about Kafka in detail. But here I am trying to show you the differences between the message queue and the event stream. Why I am doing that? Because for a long while I just assumed that Kafka lies in the category of message queue. Okay, but when I learned about the complete topic, it was like, wow, oh, I was like thinking totally wrong. Okay, now comes an important difference between message queue and the event stream. Okay, in event stream, multiple consumers can read the event. Okay, but when we talk about message queue, only one consumer can consume from the message queue. So this is a very important difference. Multiple consumers can read the event from event stream, whereas in message queue only one consumer. And another important difference between the message queue and event stream is the task remains in message queue only till the time it is not consumed by the consumer. So as we said, there is only one consumer in message queue. Once that consumer consumes that task from the message queue, that will be removed. Whereas when we talk about event stream, that event will stay in event stream even after that is consumed by the consumers. Now mostly in event stream, like when we talk about Kafka, it has retention period. It can be something like 7 days, or it can even go like 28 days. So few weeks you can also say, or a month as well, right? So you can say 7 days to like 28 30 days, that can be the retention period. So that particular event, whatever you put that in Kafka, that will stay there for whatever retention period you have kept. If you have kept like 25 days, so that event will stay there for 25 days. Even if that has been already consumed by the consumers, it will still stay there. Actually, this event is independent of the consumption. In message queue, you saw like when that task will be consumed by the consumer, that will be removed. So it is dependent on the consumption of that message. Whereas in event stream, it is independent of the consumption. Okay, as I said, like if it is consumed, still it will stay there for whatever retention period is there. On the other side, say it was present there for 25 days and no consumers consumed it. Okay, so the event is unconsumed. Still after that retention period, that is 25 days, it will be removed from the Kafka or the event stream. It will not wait for any of the consumers to consume it. So it is independent of the consumption. It just depends on the retention period, you can say. So three major differences you can clearly see. In message queue, you put the task, whereas in event stream, you put the events. In message queue, there is only one consumer. In event stream, you have multiple consumers. In message queue, the message or the task is removed once it is consumed by the consumer. In event stream, it stays for the retention period. So event stream is more durable, you can say, as compared to message queue. So this is what we have talked till now. Okay. In message queue, the producer will add the task in the queue, correct? And then consumer will consume it, but there is only one consumer. And once the consumer has consumed the task which was present in the message queue, that message will be removed from the message queue. But when we talk about event streaming, we have events that we put in Kafka. Okay, so producer will put the events in the Kafka, and there can be multiple consumers. Okay, and the event will stay in Kafka independent of the consumption of those events. It will stay there till the retention period. So basically in message queue, one consumer. In event streamings, there can be multiple consumers. Talking about the message removal, it will be removed from the message queue after consumption of the message. Whereas when we talk about the event streaming, it will stay there till the retention period. Next, if we talk about the replay message, we cannot replay the message in message queue because it will be removed once it has been consumed by the consumer. Whereas in event streaming, because the event is kept till the retention period, it can be replayed, it can be fetched again. And if we talk about the consumer state, in message queue, it is managed by the queue itself, whereas in event streaming, it is managed by the consumer because there are multiple consumers. How do they manage it? When we discuss about Kafka in detail later in this video. Now there are few more differences between message queue and event streaming as well, related to ordering and much more, but we'll not discuss about that right now because first I want to explain you about Kafka, and once you get the clarity about Kafka, then we will see bit more differences between the message queue and the event streaming. So for now, what I'll do is like I'll give you examples for both message queue and event streaming. So for message queue, you can take RabbitMQ. So Amazon's RabbitMQ is an example of message queue. And when we talk about example for event streaming, we have Kafka. So now you will say, wait, what? Is Kafka event streaming and not message queue? So here is the big question. Is Kafka message queue or event stream? Actually, Kafka can act as both, as message queue as well as the event stream, but most of the times it will act as the event streams. Now why I'm saying that you'll get to know once we talk more about Kafka. Okay, so how it works, once you understand that, at the end I can show you how it can also work as the message queue, but most of the time Kafka acts as the event streaming platform. Okay, so this is a very important thing because for a long period of time I thought like Kafka is a message queue, but actually Kafka is more about an event streaming platform. Okay, so enough of suspense. Now let's discuss about Kafka actually. Okay, so now the main question comes, what is Kafka? So Kafka is basically a log file, but it is a distributed log file. And as we discussed earlier, Kafka mostly acts as event streaming. Okay, so it will contain the events. Now Kafka has internally multiple concepts like a topic, broker, partition, consumer group, and much more. I know now you would have a lot of questions like what is a topic? How topic is different from events? What is a partition? What is a broker? What is the connection between topic, partition, and broker? What is a consumer? What is a consumer group? So many questions. That's totally fine. What we are going to do now is like I'll try to explain you Kafka with a real life practical example, and then I will relate that real life practical example with the technical details of Kafka so that you can get the complete clarity. Okay, so we are taking sports as our real life practical example. Okay, so say this is our system which keeps track of all the events related to different sports. So when we talk about different sports, you can imagine like football or FIFA. You can also imagine cricket. If you're not aware of cricket sports, then you can think it is similar as the baseball. Another sport can be the basketball, lawn tennis, F1 racing, and much more. So this system contains the events for all the different sports. So a mixture of events would be there: football, cricket, lawn tennis, racing, etc. So this system in our technical terms is acting as Kafka. So let me write down here Kafka. So in technical terms also, Kafka contain all the different types of events. Now just imagine we have like applications like CrickBuzz or CrickInfo or any other application. They basically track cricket. Okay, so these are only interested in cricket events, but here you would have all the different kinds of events, right? How can they get only cricket related events? So for that we have something called as topic. Okay, now what is a topic? Topic is basically set of similar events. For example, here you can have different events like football events, cricket events, tennis events, F1 events, and if you have any other sports, you can create a different topic for that. Now what does this represent? So for example, the football events would contain all the football related events. Similarly, when we talk about tennis events as a topic, it would create all the tennis related events. So the basic question comes, is topic same as event? The answer is no. So for example, all of these are events related to different sports like goal scored, match started, foul committed, lap completed, serve won, boundary hit. Okay, here these three can be related to football. Okay, like in football you can score a goal, match started is a common thing across different sports, foul committed is also part of the football. Okay, so these three events can be part of this topic football events, right? So a topic can contain multiple events, not only single event, it can contain multiple different events. So the topic contains a set of related events, you can say. All of these events were related to football and we have created a topic football events. So all of these events would go to the football events topic, right? So through that you can get clarity between topic and the events. Like for example, when we talk about cricket events, it can have events like boundary hit, six hit, wicket gone, wide ball, no ball, etc. So like this you can understand topic is a broad category in which you can have different set of related events. Now one question may come like, how does a event look like? So this is an example of event. You can clearly see it can contain multiple fields. Here we are talking related to the football events topic and the event is goal, or you can say goal scored. Whatever the name that you have kept for the event, that can be part of this field event. Then you can have additional information like who scored that goal. So you can have the player information, you have the match ID, like which match are we talking about, and we can also have the timestamp, and you can have few additional details as well, right? So this is an example of event. So the topic would contain multiple related events. So here in this example we said like this source contains all the events related to different sports, right? We said this system is acting as the Kafka. Then because we have different events, but the end consumer, you can say, would require some specific events. Like these applications required event related to cricket only. They don't want events related to football or tennis, right? They just want events related to cricket. So we have something like topic for that. So inside the cricket events topic, you would have all the events related to cricket only. So these applications can basically consume from only this specific topic. Now these applications act as consumers. So let me write down here consumers. Now one question may come into your mind. We said like in Kafka we will have the events, but question would be, where are these events stored? Like for example, when we talk about system design, we talked about like server acts as a machine, right? So here when we talk about like where is data physically stored, the answer to that is broker and partition. Now the question comes, what is a broker? What is a partition? So let's come back to our real life practical example, and through that let's understand what is a broker and topic. Till now we have understood this system which contains all the events of different sports is acting as Kafka. Different sports here acting as the topic, like football is acting as one topic, cricket events acting as another topic, tennis as another topic, right? And when we talk about the consumers, these are the end media products or the applications, you can say, like ClickBuzz, ClickInfo, or the media streamings, all that can be acting as the consumers. So here we said like we are talking about sports. So now the basic thing, where is this match happening? Say for example, when we talk about like FIFA game, where is that happening? That happens in a stadium, right? So let me put here stadium. Okay, so stadium is a place where the match happens. Now in technical terms, this stadium represents the broker. So in technical terms, broker is basically a machine or the server, okay, inside which you have the actual data. So in system design basics, I told you like in basic terms, server is just a machine. I mean in distributed terms, when we talk, like server is a set of powerful machines, but normally when you think in basic terms, it's just a machine. So broker also, it acts as a server, or you can say the simple machine. Now when we talk about Kafka as a system, it contains multiple brokers. Okay, so you can see here we have multiple brokers. Why do we have multiple brokers in Kafka? To avoid single point of failure. Because if we have only one broker inside Kafka, then if that broker machine goes down, your complete system would go down. But we know Kafka is a distributed system, so it needs to handle single point of failure, right? And that's why it has multiple brokers, or simply you can understand it has multiple servers or machines inside which you have the actual data. So Kafka contains multiple brokers, and combined these brokers are called as Kafka cluster. So let me write here Kafka cluster. It contains multiple brokers. Okay, or in bracket I'm writing server machine. So in Kafka you would have multiple brokers or multiple servers, multiple machines, and combined all those brokers or the machines, it is called as a Kafka cluster. Okay, so till now we have understood like stadium where match happens, it acts as a broker. Broker in simple technical terms means the server or machine. In Kafka you have many machines because you need to avoid single point of failure. Now the question comes, where do we store data inside this broker? Is it inside the topic? The answer is partition. Now what is a partition? Basically when we talk about topic, it is kind of a logical partitioning of data. Okay, it is not physical. This topic is basically logical. When we actually talk about the physical representation of distribution of data, that happens using the partition. So inside broker there can be multiple partitions, and inside partition you have the actual data. Now you would say, why do we have partition if we already have the topic, right? So as I said, topic is just logical partitioning. Partition is providing you the physical partitioning. Let me explain you that in a very simple example. Okay, say you have this suitcase, trolley bag, you can say, okay, and you have to put a lot of clothes inside it. So one way of doing that is like you have all these clothes present inside the trolley bag, right? Now you felt this bag is crossing the weight limit. Say the allowed weight was like 15 kg, or you can say 33 pounds. This was the limit of, you can say, this trolley bag. Okay, but it is exceeding that limit. So now you have one more trolley bag, say, okay, and you are allowed to take 2 trolley bags. One option would be you would take out some of the clothes from this bag and then put those clothes in this bag, right? So that is one option. You'll take out the clothes from this trolley bag and put it in this. So the other option could have been you could have used small bags inside which you could have kept the clothes. Okay, so this was one small bag. You would have one more bag out there. Okay, say like you kept like 4 small bags inside it. Okay, and in those bags you have kept the clothes. Okay, now again you feel okay, this is exceeding the limit, I need to transfer some of the clothes to the other trolley bag, right? So now it's quite easy for you. What you can easily do is like you will simply take this small bag from this trolley bag and pick this bag and put it inside this one, right? And similarly I want to pick this small bag and put it inside this. Now you both of these trolley bags have two bags and these are not exceeding any weight limit, and clearly you can see it was quite easier. Rather than picking clothes one by one, which we did here manually, we just picked the small bags, right? So in simple terms you can understand something like this. These small bags are acting as the partition inside which we are keeping the data physically. Okay, so this complete is acting as, you can say, the broker. This was one broker, this is the second broker. Different machines inside which you have kept the data, and through the partitions it is making your life much more simpler, sorted and easier, because a machine, the broker, can contain a lot of data, events of different topics as well. So the machine can also contain information of football events, the cricket events. Then again it will become messy because we want some specific data, and for that we have things like topic and partition. Topic is acting as the logical distribution, whereas partition is acting as the physical distribution of data inside which the actual data actually is present. Okay, so going back to our sports example, just imagine if we are talking about like the cricket events topic. Okay, so this was your topic and we said like it can have events like boundary hit, 6 hit, given out, wide ball, no ball, etc. Right? So all those are the events related to cricket. That is totally fine. But just imagine there can be a lot of matches that can be happening for cricket. Like for example, currently the World Cup is going on. You have match like India versus Pakistan, Australia versus England, USA versus Nepal. So you have so many matches that are happening. Okay, and the applications need to show the data for each of the match. Now this was just one topic, but we need information of different matches, right? So how do we handle that? Basically, as I said, this is just a logical distribution. You just simply said it will contain all the data related to cricket, but physically those events would be present in the partition. So it can be something like this. Okay, this is your broker. Okay, broker is representing your machine or server. Okay, so inside the broker you can have multiple partitions inside which the data will be present. So it can be your partition 0, like the ID you can say P0, this can be your P1, this can be your P2. So clearly you can see the machine or the server can have multiple partitions inside it. Okay, and each of the partition will have the events related to a topic. Like for example, this partition can have the events related to the cricket related topic, right? And this can have related to football. Okay, so different partitions can have the events related to different topics, right? So it is not like that broker will contain the events of only one topic. Okay, so this is clearing a very important question. The question is, can a broker contain multiple partitions? Of course, yes. We have said like inside a broker you can have multiple partitions. Another question, can a broker contain events of different topics? The answer is yes. I mean, technically it becomes difficult to understand. So let me tell you it with a very simple example. We said like broker is acting as the stadium, right? Stadium in which the actual match happens. Now the same stadium can be used to play different sports. You might have seen the same place is used for multiple events. You can play FIFA match on it as well. You can play cricket as well, or any other sports which require just a ground or stadium. Of course, you need some more accessory, like for FIFA you would require that goal stand and everything. For cricket you would require a pitch, but you can create that kind of thing in the same stadium. So the same stadium can host different sports, right? Even when we talk about Olympic or Commonwealth games, you have specific stadiums, and in that stadium multiple sports happen, right? So similarly, in a broker or a machine or a server, you can have events related to multiple topics. Okay, that's why we need the partition, because otherwise all the data will become like messy. All the events are present of different sports in the same machine, and it becomes difficult for you. And that is solved by the partition and topic is just the logical thing, but actually you can clearly see inside broker we have kept the partition which contains the events physically. Okay, to make this example more easier to understand, let's just imagine all of these partition are keeping data related to one sport. Say we are saying like cricket. Okay, so all three partitions are keeping data for cricket events. Okay, now as we said, there can be multiple matches which can be happening. So like match 1 is like India versus Pakistan. Okay, and then the match 2 can be Australia versus England, right? So something like this, you can imagine there are multiple matches happening as the World Cup is going on for cricket. Okay, so now these partitions will keep track of different matches. How will they do that? Like very similar to what we do in normal system design, we use techniques like hashing, right, to distribute the load. Similarly here we will use basically the hashing, you can say. Partition 0 is taking care of like match 0, match 3 and match 6. Okay, partition 1 is taking care of match 1, match 4 and match 7, right? And talking about partition 2, it is taking care of match 2, match 5 and match 8, right? So clearly you can see we have distributed the load here, and one partition can take care of multiple matches. So events related to multiple matches are going to one particular partition. Now through the partitions you can see how Kafka is distributed system and how we are maintaining the asynchronous processing, right? If all the data was present in just one place, it would have been difficult for the consumers to consume the events. Now because of partition, what happens is like multiple consumers can consume from partition 0. Similarly, multiple consumers can consume from partition 1. Right? So these are kind of independent of each other now. Now one question would come, like in brokers, we said like we are avoiding single point of failure. That is why we have multiple brokers inside the Kafka. What about the partition? What if this P0 fails? How can we avoid single point of failure here? So the answer is Kafka already takes care of this. Basically, whenever we talk about one partition, Kafka also has the replicas for that partition. Okay, say for example, when we talk about P0 here, right? So for P0, there is a concept called as the replication count, which we will discuss later in this video. Don't worry about it. But say the replication count is 3. Okay, so that many number of replicas would be present for partition 0, and that would be present in different brokers, right? So you're keeping the replicas or the duplicate copies in different machines so that we are properly avoiding single point of failure. Because what if you have all the replicas in the same machine and that machine broker goes down? Then you are not doing it very nicely, right? So that's why we keep the replicas in different machines. So we will talk about that later, don't worry. I just wanted to give you a broader picture that Kafka is a distributed system. It takes care of all of such things already. So here one thing you can clearly see, we are not creating the partition just based on individual match. It's not like that P0 is just defined for match 0. Okay, it's nothing like that. One partition can contain events for multiple matches here if we are talking about this example, right? Now one question would come into your mind, how about the ordering of events, right? For example, the player hit the 6 runs and then the player got out. We need to maintain the ordering because a player cannot hit 6 after getting out, right? It's very simple. So we need to maintain that order. So how do we maintain the ordering in partition? Also, do we maintain the ordering across multiple or different partitions? All right, let's try to understand this. So we said like we will use some concept like, say for example, we are using hashing, and based on that in partition 0, all the events for match 0, match 3, match 6 are going here, right? Here basically I used a very simple hashing function, like say for example, the total number of partitions here were 3. So I'm just doing the modulus with 3. Okay, so M0 is going here, M1 is going here because the remainder comes as 1 here, so going to partition 1, and then M2 here, and then basically M3 comes here again because the modulus gives 0, so we are assigning to P0, right? So here I have assigned basically a simple hashing function, okay, through which we are assigning the partition ID to the match, right? So basically important thing here, based on the match ID, like for example this was one example of the event, right? It contained the match ID. So if your event contains some ID, on basis on that ID we can do the hashing, okay? Say for example the match ID would be 0, 1, 2, all those match IDs. Based on that you can perform the hashing, and then you can assign the particular partition based on that, right? So if we are getting some particular ID in the event through which we want assignment of the partition, we can do that using the hashing function. And if that's happening, you can clearly see all the events of match 0 are going to partition 0, and hence all the events related to match 0 will be in order, because we are maintaining the order. In Kafka it's like a distributed log file, and all the operations are like append at the end of the file, okay? So you are just appending data at the end, so all the events are getting appended at the end. So that's why the order is maintained. When we talk about like match 0, say a player hit 6 runs, so you get that event first, and then the next event would be the player got out, so that would come later, okay? So that is already maintained because all of the events related to match 0 are going to partition 0, and hence the order is getting maintained for all of the events, okay? But now the other question, when we talk about like different partitions P0 and P1, do we maintain the order in that as well? The answer is no, okay? These are acting as like independently, okay? So in case they need to maintain the order, they would have to sync with each other, and that would be too much of work. That would slow down the thing and cause strong coupling and much more things. We don't want that, and hence in Kafka the ordering is maintained in a particular partition, but ordering is not maintained across multiple partitions, okay? And that makes sense. For example, this partition P0 contains the events of match 0, whereas for partition 1 we have the events for match 1. So we don't need to maintain the order between match 0 and match 1, because those are different matches, different things are happening there. You don't need to maintain the events in that. Ordering matters when we are talking about a particular thing, okay? So match 0, if we are talking about, ordering matters, and that is handled by Kafka, because the ID that we are getting inside the event, through that we assign it to particular partition only. Now question might come like, what if this P0 is down? Even then it's totally fine, because we already have replicas. One partition, which is the leader partition, you can say, it goes down. From the replica, one of the replica will be assigned as the leader, and all the writes and reads happen from the leader only. So if P0 was active, it was the leader, all the writes were happening to it, all the reads were happening from it. But in case P0 is down, one of the replicas will be assigned as a leader, and the write will happen in that, read will also happen from that. So it totally works that way. But what if you are not getting the ID inside the event? Then how would the distribution happen? So it's very simple. In case you need the ordering, okay, so for example for match 0 you want to maintain the order, you should pass the ID in the event, because based on that you will assign the partition, and always for a particular event ID it will go to the correct partition, so order will be maintained. In that case it can be assigned to a partition like round robin approach, you can say. First event goes to P0, then P1, P2. I mean, there can be other approaches as well, but that is decided by Kafka. But because we are not passing the event ID inside the event, so we don't care about the ordering in that case, and that's fine. Okay. All right. So this was like a brief of the partition, okay, through the real life example. So coming back to this example, the stadium in which the match happens act as a broker. Inside the broker we have the partitions in which you store the actual data, okay? So partition would contain the data like for match 0, match 3, match 6, so like that. Topic is acting as like which sports we are talking about here, so the logical distribution of data, you can say. So in this example term, broker is the stadium, partition is the different matches happening, and then the end applications or the media streamers are acting as the consumers. So these are the consumers, but the question comes, who is the producer here? So if we talk about this example, the referee, okay, or the umpire is acting as the producer, right? In each of the match, you either have the referee or umpire. The umpire in cricket would give out or six or boundary or wide, no ball. So that is acting as a producer. Through that, you get the events, and then those events are stored inside the partition inside the broker. Okay, so we got the brief idea about the broker, topic, partition, consumers, right? But apart from this, there is one more concept in Kafka, which is consumer group. Now the question comes, what is a consumer group? So let's again try to understand that with a simple example. Okay, say the name is like crick update. Okay, so it will give you the score updates related to cricket. Okay, so this is basically consuming the events from Kafka, you can understand, right? Cricket related events. So the topic from which it is consuming is the cricket events, right? Now let's say this consumer, like this business, you can say it has like 3 employees, correct? So all of these 3 employee basically keep a track of the cricket matches which are happening. So in the Kafka, you have all the data. So these are basically checking the cricket matches and fetching the data and updating their own, you can say, database or whatever they have system, right? So just imagine all 3 of these are basically checking like match 0. Okay, and they are keeping a track on what is the event that is happening. And let's say there was an event like out happened or some event happened, right? So all 3 of these check that. There can be a case like 2 of these employees updated that in the DB. So one said like out, another said like out, because they were consuming from the system, and out was an event that happened. So but multiple employees picked the same event and modified the things in their on DB or whatever you can say, right? So this is an issue, right? Sometimes what we want is like, this is one unit, this is acting as a single unit, and what we want is like only one of these should be able to consume the events, right? Because you can clearly see if multiple people or employees are working on the same event, there is a high probability they would mess it up. And it is also not like optimized, because there are 3 employees, they should be able to check the events from multiple partitions, right? So that's where we have the concept like a consumer group. So this is acting as one consumer group. So the logic in consumer group is like, say there are partitions, right? This is partition 0, this is partition 1, and this is partition 2. Okay, so say for example we have 3 partitions, and of course, as we said, one partition can cover multiple matches, right? So when we talk about the consumer group, the basic funda of consumer group is that only one of the consumer inside the consumer groups. So this was acting as one consumer group, these are acting as the consumers because these are consuming events, right? So only one of the consumer from the consumer group can consume from a partition. Okay, so it's very basic, like if this is one company crick update, it is acting as one consumer group. So only one of the employee can basically consume from partition 0. It's not like if employee 1 is consuming from partition 0, then employee 2 is also consuming. That is not allowed. Only one of the consumers inside the consumer group can consume the event from a partition. Now what's the use of it? It is very useful because, say for example, consumer 1 or the employee 1 can consume the events from partition 0. E2 can consume from partition 1, and E3 can basically consume from partition 2. All of these are covering different matches. Okay, so through this you are basically increasing the productivity as well. This is a distributed system, there is asynchronous processing. So through this you are able to maintain the things, right? So multiple consumers are able to consume from multiple partitions here. But only point of consumer group is that when we talk about a consumer group, the consumers present inside the consumer group, only one of the consumer can consume from a particular partition. I know it can become difficult to remember, so you can remember in terms of this real life example. This makes more sense. Like in a company, multiple employees work on different things, right? So it's not like 4 employees are just focusing on one match, because that is not productive and that can also result in the duplicate results. We don't want that. So in a consumer group, only one consumer is allowed to consume from one partition, right? Now don't confuse it that E1 can only consume from partition 0. One consumer can consume from multiple partitions. That's the beauty of Kafka, right? It's a distributed system. There is asynchronous processing and you can have multiple consumers. That is why it is event streaming and not message queue. You can have multiple consumers. So this consumer can consume from multiple partitions. That is totally fine. But when we talk about consumer group, this is one group. Okay. So inside this, the consumers, if we talk about partition 0, only one will be able to consume from one partition. Okay. And now apart from this, say for example, there is a different consumer group. Okay. This can also consume from P0. That is totally fine. So clearly you see here, partition 0 is being consumed by multiple consumers. That's the beauty of Kafka. That's even streaming. But these consumers should not be part of single consumer group. These are part of different consumer groups. Okay. So you can simply understand like this is quick update application. This is quick tracker applications or different applications they are consuming. It's totally fine. Right. So this was kind of like a real life example through which you can easily relate. First of all, you don't need to remember like completely, because generally when we talk about Kafka, you just need to know why you use Kafka. But here in this video, we are talking in detail like how Kafka is basically working. You don't need to remember everything, but yeah, using this example, I think you can easily remind yourself the concepts. It becomes very easy. Like just imagine if you talk about broker, partition, topic, oh my god, I don't understand. And then if you talk in simple terms, simple server machine broker. Kafka contains multiple brokers because of course we are talking about avoiding single point of failure. So Kafka would contain multiple machines. So you have multiple brokers. Topic is just like logical partitioning. Like instead of having all the events like football, cricket, on so many events present in one machine, you just make the logical partitioning. This is related to cricket, this is related to football, this is related to lawn tennis, right? It makes things so easier. And then partition, because in cricket also you would have so many matches, right? So you have partition, which is like physical distribution of data. Inside broker you can have multiple partitions, and partition would take care of multiple matches, you can say, right? And then you have of course the consumers as the applications, like the Hotstar is there, ESPN, Cricinfo is there, Crickbuzz is there, so many. And these are the consumers. And when we talk about the consumer group, you can just imagine it as like inside a company like ESPN, Cricinfo, there are multiple employees. You don't want all the employees focus on just one match and they are just duplicating the data. It makes no sense. So all of the employees are working on different matches because they can consume event from multiple partitions. Sounds good? Okay, so one more thing about consumer group and consumer in Kafka is that a consumer cannot exist without any consumer group. Okay, so say for example, you have something like this in mind, like this is consumer 1 and this is consumer 2. Now you are saying like both of these are not related. Okay, so you have just defined consumer 1, consumer 2, but actually as I said in Kafka, a consumer cannot exist without consumer group. So by default what will happen is this will be part of first consumer group, so you can say CG1, and this would be part of another consumer group, say CG2. Okay, so by default Kafka creates consumer group. A consumer cannot exist without a consumer group. So in a consumer group you can have one or multiple consumers, but one consumer will be part of only one consumer group. Now it can be difficult for you to remember, but if you think in practical or real life terms, it becomes easy, because an employee will be always part of some company, right? If you're employed, like you'll be part of some company, right? So company is acting as the consumer group and the employee is acting as the consumer. So like we discussed for the sports, right? So Crickbuzz acts as one of the consumer group, and inside that the multiple employees who are part of ClickBus company act as the consumers. So this is helpful in scaling because now we have multiple consumers in a consumer group. These consumers can consume from different partitions. So that helps in scalability. Okay. So overall, we talked about some of the concepts in Kafka, like using a real life practical example. Now let us go through all of these in more technical terms. So first, when we talk about a topic, as we discussed in the practical example, like we took like cricket events as one topic, football events as another topic. So a topic is a category or stream of events. So if we take technical examples, we can have order events, user activity, or payment related events. These are examples of the topic. So a topic would contain related events. Like when we are talking about orders related topic, it would contain all the events related to order. So the basic question that comes into mind, are topic and event the same? The answer is no, they are not same. So basically a topic is a named stream or category, whereas event is a single fact that happened. So inside a topic, you can have multiple events. Like for example, we discussed topic related to cricket. It can contain events like given out, six, boundary, wide, no ball, etc. So you can see there are so many events, but because these events are related, they are part of one topic, which is cricket. Now let's talk about a technical example. So Kafka is also used in designing YouTube. You can refer to this video of mine where I've discussed in detail about designing YouTube, and in this video we have used Kafka as well. So you can refer for more details. But just to give you a summary, basically you can imagine our topic could be something like system design videos, and it can contain events like video uploaded, video viewed, video liked, video commented. So all of these events are related to the topic that we have related to the videos. So each of these event is published to the same topic that we have, or similarly we can also have different events which can relate to some other topic as well, right? So a topic can contain multiple events, and it's not like you will have only one event type. Clearly you can see you can have different events as well, which are part of the same topic. Another technical example would be here, as we said, like orders event can be one of the topic when we talk about shopping related application, right? So this is the topic, but it can contain different events like order placed, order cancelled, right? So here you can see when we talk about the topic order events, it can contain different events. Like one of the event can be order created. It has more information as well, like order ID, user ID, and the amount. Similarly, there can be one more event like order cancelled with the order ID, user ID. So both of these events will be part of this topic order events. Hence topic and event are not same. A topic can contain multiple stream of events. Now after topic, let's discuss about partition. So basically, as we discussed earlier, a broker can have multiple partitions. Even when we talk about a topic, like for example, we took cricket as a topic, right? So that was one topic, but it would have multiple partitions. So similarly, say the topic is orders, it can have multiple partitions. Okay, so a topic is split into multiple partitions. Although topic is just logical representation, whereas partition represents the actual physical distribution in which the events would be present, right? And when we talk about each of the partition, it is an ordered log, which means all the events inside a particular partition, in that the order will be maintained. For example, we talked like, see, there are three partitions, P0, P1 and P2, right? So these were the three partitions, and we also mentioned that, say, P0 is taking care of match 0, match 3, match 6, right? So all the events which are coming with the ID, okay, say for example, any ID related to match 0, that event will come to this partition, right? How that happens we'll discuss later, but it will come here. Next, another event comes for match 0, it will again be part of this partition 0. So inside a partition, order is maintained in a particular partition, but order is not maintained across partitions, okay? Or you can say across the topic it is not maintained, because all of these three partitions could be related to the same topic, say orders topic or cricket events, you can say. So in the complete topic, ordering is not maintained, but in a particular partition, ordering is maintained. And in each of the partition, the events are stored on disk and those are written sequentially. So basically the role of partition is to provide scalability, parallel processing, load balancing, high throughput. We will discuss how that is happening later in this video. Now one important thing is like topic is just a logical name, okay, whereas partition is the physical storage. So topics do not store the data themselves, but partitions do, right? As we discussed earlier, topics are just for the logical distribution, whereas partitions do the actual physical distribution. Now a question may come into your mind, what is the relation between a topic and partition? So basically we understood, first of all, topic is a logical name, whereas partition is the physical storage. Another type of mapping is like here you can see the topic is orders, but for that we have multiple partitions. So a topic could contain multiple partitions, and through multiple partitions only we are able to provide high scalability, high throughput, parallel reads. All that is happening due to multiple partitions, okay? But a partition can be part of only one topic, okay? A topic can contain multiple partitions, but a partition would be part of only one topic. A partition cannot be part of multiple topics. Like for example, we discussed for the cricket events, there can be multiple partitions, right? So those will be handling multiple matches, but those partitions are handling events related to cricket only. It can't be the case like for the cricket events topic, we have created two partitions, P0 and P1, but P1 is also taking the events for related to football. That is not possible here. These partitions which are part of cricket events topic, these will take events only related to cricket. So a partition will only correspond to one topic, whereas a topic can contain multiple partitions. Now one question would come into your mind like, why do we need partition if we already have the topic? So I explained it to you using that suitcase example, right? So if you have suitcase and if you keep the clothes directly into it, whereas there is one more case like inside the suitcase you can keep small bags, and inside the bag you can keep the clothes, right? When you maintain small bags inside the suitcase, that is really helpful if you need to transfer some of the stuff from one bag to another bag. You can simply pick one of the small bag and shift it to the other one. That is the kind of role of partition. But let's try to understand that in more technical terms. So as we said earlier, topic is just logical, so it is not actually a storage, okay? So it is just a logical names. So in order to store the events, you would require the physical storage, and that's where partitions come into picture. You can think of it as like topic is the folder name and partition is the actual files that are present inside the folder. Now you cannot write data into a folder, you write data into the files. Similarly, when you have to keep the events, you put it into the physical storage, that is the partitions. Now let's just imagine like we have the topic as orders, and inside that we have like a single log file. Then there would be a lot of problems related to it because this is not scalable, right? Because you have only one log file, it contains all the information. Like we took the cricket events example, so many matches happening, so only one file contains all that data. If there is only one file, you can imagine we can't scale it, there is no throughput, there is no efficiency. And also it acts as like single point of failure. If that dies, your complete system is gone. So in order to provide scalability, parallelism, fault tolerance, and in order to avoid single point of failure, you have partitions. Now we talked about these problems, right? Using partitions, we can solve it. Like we can make our system scalable. How? Basically, we mentioned like there can be multiple partitions for a topic, right? So each of the partition can exist on a different broker. So we can have multiple partitions for a topic, right? Like for cricket events, we had multiple partitions. So each of these partition is independent of each other. Like this one had the information related match 0, match 3, match 6. This had information of match 1, match 4, match 7, right? So these are independent of each other, and these can live in different broker. Whereas if we see the case of single log file, that all complete data would be present in only one machine. Whereas now you can see you have distributed the data, and that data can be present on different machine. Like this can be part of different machine, and this one can be part of different machine. And now different consumers can consume. Like some consumers can consume from this, some consumers can consume from this as per the requirement, correct? By this you are also balancing the load, because say the consumer wants to track only for match 1, so they don't need to consume from this partition 0 because it does not have the data related to match 1. Match 1 related data is present in partition 1, so you can simply consume from that, right? So you are also balancing the load, and you are also avoiding single point of failure, because now these are present in different machines, and as these are independent of each other, you can scale them independently. Also another point of parallelism, like here we have 3 partitions, right? So in parallel, different consumers can consume from different partitions. So from every consumer group, one consumer can consume this partition, and then some other consumer from that consumer group can consume this partition. So it increases the parallelism. Now one important thing is, like, topic and partitions are related. So whenever you create a topic, you need to mention how many partitions do you require. So now a question may come into your mind, and the question would be, how do we add a new topic and who adds it? So there are multiple ways to create a topic, and a topic can be created by an operator, developer, or the platform team. It can also be created automatically by Kafka, but that is not recommended when we talk about the serious setups. So the most common way to create a topic would be using the API or CLI. Okay, so you can download and install Kafka on your machine, and then using this command you can create a topic in Kafka. So you can clearly see what we have done here. We have mentioned hyphen create, and then after that a backslash, and then we write hyphen topic, and then the name of the topic. Okay, so here the topic name is orders. This is the property and this is the name, you can say. So the topic name is orders. Here we can keep any topic name, and then as I said, while creating the topic you also need to mention number of partitions required. So next you also provide partitions count, which is 6 here. So we have asked for 6 partitions. So for orders topic we will have 6 partitions. So something like this you can imagine. So we are talking about the orders topic here, right? And we would have the 6 partitions: 1, 2, 3, 4, 5, 6, right? So 6 partitions are present for this topic. The topic is logical, but the partitions are physical, in which the events will be stored. Next, when we create the topic, we also provide the replication factor. Why is replication required? To avoid single point of failure. So for every partition we would have this many number of replicas. We will discuss about replicas later in this video, because I don't want to complicate things for you for now, but you can just imagine, like, if we have kept the count of partitions as 6 here, so you have 6 partitions here. For each of the partition you will have the replica, so that in case this partition is down, the replica can take place of this, because you know these partitions are independent of each other. So this partition won't be able to do the things this partition is doing. So we need replica for each of the partition to avoid single point of failure. Okay, so I just gave you the brief, like how can you create a topic, so that it gives you a bit clarity. Okay, we can do in this way. And you can clearly see it's not that difficult. It's really simple command that you put, and through this you will be able to create a topic, whatever name you want to give to the topic, and the partition count and the replica factors. Now before going in more detail in this, I want to cover a very important topic which should be clear in your mind. Okay, because when we talk about Kafka, we also want to know like how the events are consumed. We don't want to be restricted only about like what all the things that are present in Kafka. We also want to know basically how consumers are using the events, right? So let's cover that part first, and then again I'll deep dive into all the components of Kafka. Okay, in the broker we have like 3 partitions. Okay, this is P0, this is P1, and this is P2. So I have just assigned some IDs so that you can differentiate the partitions. These partitions can be related to one topic on different topics as well, because in a broker you can have multiple partitions and a broker can cover multiple topics as well, right? So I'm keeping that aside. Just keep in mind like you have 3 partitions here, right? And now let's also talk about the consumers, because we want to see how the events are consumed. So imagine like this is like consumer 1, and say this is part of like consumer group 1, okay, CG1. So consumer 1, which is part of consumer group 1. Okay, and then let me create one more consumer group here. Okay, so this is CG2, right? So this is a different consumer group, and say inside this we have like consumers C2 and C3. Okay, let me also form for this one. Okay, so here you can see we have two consumer groups. Like this we can have many more consumer groups, and inside consumer group 1 we have consumer 1, inside consumer group 2 we have two consumers. Okay, as I told you earlier, a consumer cannot exist without a consumer group. So just in case in future you put it like we have only one consumer, just imagine it is part of some consumer group. You don't need to always say that. It's a basic thing that automatically a consumer group would be there. Okay, but a generic term generally we use is like consumer is consuming. But overall in your mind you should know, when we are talking about consumer group, only one of the consumer inside the consumer group can consume from a particular partition. Like what I mean is like both C2 and C3 cannot consume from P0. Okay, that's a rule of consumer group. Although this is allowed that C2 can consume from P0 and C3 can consume from P1, because these are different partitions and we allow parallelism, scalability in Kafka. So that is totally allowed, but both of these cannot consume from the same partition, because that causes issues like we discussed. If two employees are tracking one match, then there can be issues like they are not being productive and there can be a lot of duplicate effort. Okay, which we don't want, right? So here what I want to tell you is like, now just imagine consumer 1 is consuming events from partition 1. Okay, and because in Kafka we allow parallelism, there is scalability and there can be multiple consumers. So in this example what we are going to do is like say C3 is also consuming from partition 1. Now this is totally fine. What is not allowed is, because C3 is consuming from P1, C2 also cannot consume from P1, because C2 and C3 are part of same consumer group, whereas C1 and C3 are allowed to consume from P1 because these are part of different consumer groups, right? So you can imagine these are employees of different companies, so that is totally allowed, correct? So the main part is there can be multiple consumers to the events which are present in the same partition, right? So that's the beauty of Kafka, and that's why Kafka most of the time acts as event streaming and not message queue, because if this setup was message queue, then for this there can be only one consumer. That's the rule of message queue, there can be one consumer. But when we talk about event streaming, there can be multiple consumers, and that's the example we are seeing here. C1 is also consuming from P1, C3 is also consuming from P1. Now the major question comes, how multiple consumers are able to consume the events from Kafka? The most beautiful part of Kafka is like both of these are independent of each other. So they are able to consume the events independently. It's not like if C1 is consuming, C3 also needs to consume that. No, these are independent of each other. But how is that working? That happens due to the concept called as offset. Now what is an offset? So basically, as we know, the events are stored inside the partition, right? So, and each of the event you can say assigned an offset. Say for example, the first event offset would be 0, then 1, then 2, then 3. You can simply think of offset as an identifier or number through which you can uniquely differentiate the event, right? So this is the definition of offset, a monotonically increasing number that uniquely identifies a record within a partition. So in very basic terms, offset would be present per consumer per partition. Okay, so for example, consumer 1 is consuming from P1, so it will have its own offset, whereas C3 will have its own offset for P1. Why? Because both of these are part of different consumer groups, and I said offset would be present per consumer group per partition, right? Why did I say per consumer group? Because I said both of these can consume the events independently. And why did I say consumer group? Because you know, like C2 and C3 cannot consume from same partition, right? That's the rule. So that makes sense. You can simply say per consumer or per consumer group we will have a offset so that they can operate independently. Okay, I'll explain it to you in very easy way. Don't worry about it, you'll get all the doubts cleared, but just go with me for a few minutes. Okay, and then I also said per partition. So let me write that first, per consumer group. and per partition. Okay, let me try to explain you in easy way, then we will come to this philosophy. Okay, so what offset represents here? So as I said, every event or record will have some number. So you can simply say increasing numbers through which we can clearly identify every record, right? But there is more to it. Now say for example, C1 says for P1 the offset is 20 and C3 says for P1 the offset is 34. Okay, what does this mean now? It simply means that C1 wants to consume the events from P1 20 onwards. Okay, so as we gave the number to each of the record, so you can just imagine there can be so many records, like this is 0 and it goes on, here comes like 20th record, right? And then after also there are many records, and then there also comes like 34 is there, and then also there are multiple records. So when C1 says the offset for P1 partition 1 is 20, it means C1 wants to consume the events from 20 onwards. It means that consumer 1 has consumed the events till 20 of partition 1, but it wants more events after 20. And when C3 says 34 as the offset for partition 1, it means it already has the data or events before this number and it wants the events from partition 1 34 onwards. Okay, so offset is representing from where we want to consume the events. From here onwards we want the events, because before this we already have the events. We want the data or events after this number, which is the offset. Okay, so now why did we say like per consumer group? Because I said you earlier, the main point of Kafka is all of the consumers consuming events are independent of each other. So C1 can read from here, whereas C3 can read from here. So they are independent. It's not like if C1 is reading from this point, C3 also needs to read from this point. These you can simply imagine in technical terms different microservices. Okay, so say this is payment microservice and say this is profile microservice. Okay, and these are independent of each other. That's why we follow the microservice architecture, right? So their functionality, their working and their requirements would differ, and that's why we have offset, so that this microservice can consume from wherever it wants to, because before that it has already consumed, and whereas this is totally independent of this microservice, this can consume from some other point. Okay, so that's why we have per consumer, or you can say per consumer group. And then why we say per partition? Because in Kafka one consumer can consume from multiple partitions. So for example, when we talk about C3, it is consuming from partition 1. It can also consume from partition 2. Okay, and it can also consume from some other broker with some partition present in it. Okay, so it is totally allowed that a consumer can consume from multiple partitions. That's a wonderful thing about Kafka. You can have multiple consumers, not only for one partition, for different partitions. Similarly, like C1 was consuming events from P1, it can also consume events from P0. That's totally fine. And similarly for C2, it can consume from any partition as well. Now C2 of course cannot consume from partition 1 and partition 2, because C3 is also already consuming from it. So we can imagine something like C2 can consume from P0. That is totally fine. And like it can also consume from some other broker partition as well. Okay, that's totally fine. Here you can see why we put like per partition, because like we took the case of C3, right? C3 has like offset of 34 for partition 1, but now we said like C3 is also consuming from partition 2. It does not need to pick, so it can have a different offset for that. It won't be 34 there, right? Because this is some other data. P1 has some other data, P2 has some other data. So for example, here you can say the offset is like 71 or any offset. It can have different offsets. So clearly you can see per consumer, per partition. Okay, so we have the offset, and using offset, it becomes possible that consumers can consume independently, right? So consumer 1 is consuming at like offset 20 from partition 1, whereas consumer 3 is consuming from the same partition from different offset. And offset represents like C3 wants the events from number 34 onwards. So events with number 34 onwards it wants, because before that it already has those events. So as I said, like offset would be per consumer per partition. Per partition means like the offset for P1 is not at all related to the offset of P2, because these are dealing with different things, different events, so their offsets are also independent of each other. So as we discussed, what does an offset represent? An offset is basically a bookmark, you can say, and which says I have successfully processed all messages before this offset, right? When we say like 20 as offset, it means like I have already processed the messages or events before 20. Now that we have talked about offset, one question that might come into your mind is like, where are offsets stored and who stores the offset? So the answer is offsets are stored in Kafka itself. So we are talking about Kafka. Inside Kafka we have the brokers. Inside a broker you can have multiple partitions, and per partition, per consumer group, you will have the offset, right? And we will store the offset in Kafka itself. And as we are talking about topics, right, for this, for storing the offsets also, we have an internal topic in Kafka. That internal topic is consumer offsets. Okay, so it's not like if you have different consumer groups here, you can simply imagine this is a microservice, this is also a different microservice. These are not storing the offsets. Okay, the offsets are stored in Kafka itself, and the topic name for that is consumer offsets. Now why this makes sense? Because Kafka is durable. Okay, as we discussed in the beginning, Kafka acts as an event stream, and it is different from message queue in multiple ways. Two major differences, like there can be multiple consumers like we saw, and one more important point was like you can, data stays in Kafka till the retention period, right? So Kafka is durable, so it totally makes sense if we store the offsets in Kafka itself. And then offsets are also replicated, and it can survive the consumer crash. Now why does it make sense to keep the offset in Kafka itself using this consumer offsets? Let me explain it to you in easy terms. So simply assume this is the Kafka. Inside this you have the partition and everything. Okay, and this is your first microservice acting as one of the consumer, and this is another microservice. So different consumer groups. So we are talking about one partition here. Okay, so just imagine this is a partition, and both of these consume from this group. You can keep more consumers. So let's say there are 3 microservices, so 3 different consumer groups, and these are consuming a particular partition here. Okay, so as we said, like the offset would be per consumer group per partition. So if we are talking about this partition, for this consumer group, the offset would be present in this topic consumer offsets. Say for this it's like 20, and say for this one it's like 13, and say for this one we have like 47. Okay, so all of these will have an offset because these are different consumer groups, and offsets are per consumer group per partition. Okay, so this is the partition, say P0. Right now, simply let's say this microservice got the offset from this topic of Kafka consumer offset, right? It gets that. Now it will try to consume the events after 20, right? And similarly this will try to consume the events after 13, and this one after 47. Although the timing can vary because all of these are independent of each other, so it's totally up to them when they want to consume the event. And of course offsets are also different, so that's why these are independent, right? So let's say this microservice is trying to consume the events from 20 onwards. It fetches the events from Kafka, and it was performing some task, and then let's say it crashes. Okay, this microservice crashes. So this component, this consumer group, whatever you want to say, this crashes and it is not able to perform the task completely. So what will happen now? How are we handling the failure scenario here? The great part of Kafka is that, as we said, the events will stay in Kafka till the retention periods. So let's say the event was added today and the retention period is like 28 days. Okay, so the event will stay in the Kafka for 28 days, irrespective of the fact that this consumer has already consumed that event, or this one, or this one, or all of these consumer have consumed or not consumed, this event will stay in Kafka for 28 days. So this provides the durability factor. So even though it crashed, when it comes back, it is healthy again. What it can do is like it can simply again fetch it from this topic consumer offset, and it will return 20 again, because this offset is per partition, which is P0, and per consumer group, so this consumer group. So for this we already have this value 20 present here, correct? So it will again get this offset as 20, and then it will try to consume the events 20 onwards from Kafka, and then again it will try to perform its task. Now in case it's successful, it's the duty of this consumer group or this microservice, which is acting as a consumer group here, to update this offset in the Kafka. So once the consumer group is completely able to perform its task, like from 20, say it took like 10 events, so 20 to 30 it took the events, and say it performed all the tasks. Task can be anything. So say for example we are talking about YouTube and it's about the like on the video, so it can pick all those events. Based on that it can do whatever calculation it wants to do. It can update the DB in a batch or whatever, all those things, right? You can refer to these video, you'll see the roles that Kafka is playing, right, in detail. But here simply imagine it is doing some task, and once it is totally able to perform that task, it is able to complete that. What it needs to do is like it's the duty of consumer group to update this offset in Kafka. So what it will do is like it will make a commit for the offset. So it will set the offset to 30 now, because it has consumed the events till 30, and once it has committed that in Kafka inside this, for this particular consumer group and partition, the offset will become 30. So the use of this is, next time when this consumer group asks for the offset again from the Kafka from this topic, it will return the offset as 30 and not 20, because now events till 30 have been processed by this consumer group for partition P0. Okay, so the use of keeping this inside consumer offsets topic is that it is really durable. You have seen I discussed the both happy flow and the failure case. Happy flow looks totally fine, you are consuming events, and it's the role of or the duty of consumer group to update that or commit that updated value of offset to this consumer, to this topic of Kafka, right? And in case it fails, it's totally fine. That data will stay in Kafka because Kafka is reliable. It is durable. Generally in Kafka, we talk about the retention period, right? Like 28 days and everything. For this particular topic, I think the retention period rules are not applicable. The data remains in this because it just maintains the latest offset. It's not like earlier it was 20 and now it's 30. So it is maintaining two records for this. Per partition, per consumer group, there is one record only. And it is like earlier the value was 20 and now the value is 30. So there is only one record per partition per consumer group. So it's not like you are getting huge amount of data, right? It's just the combination of partition and the consumer group, and there is only one value for that. So this topic stays there in Kafka. It is an internal topic, and in some of the documentations it is mentioned that it doesn't even require the retention period. It stays there because it is maintaining the offset. But yeah, there are few other things also that can be done. You can till sometime it is not updated, you can reset the offsets, and there are some other things, but we don't need to go in detail for that. You can just imagine this topic remains there. You can just imagine like it has some life, so you don't have to worry, oh my offsets will be gone. It's not like that. And also we keep the replicas of the offset, so it is very much durable, okay, and quite safe, right? So we talked about the failure scenario, and that's a really important case to understand. So if I tell you again for this scenario, like this consumer group tries to consume the events 47 number onwards because it gets that value from this topic, which would be unique for partition and this consumer group, right? So it gets 47 and it will say it took like 7 events. So 47 to 54, it consumed the events and it is processing that. And during that time, some failure scenario happened and it was not able to completely process that. So of course, it will not commit that number, right? So the old value will remain in Kafka. So it will only remain as 47. So next time when this system is up, this consumer group again tries to fetch the offset from this topic, and 47 will be returned to it again. So again it will fetch, like, consume the events from 47 to 54, whatever the limit it wants, and then it will process those. Once it processes those successfully, it will update this offset to 54 because it has consumed the events till this number. And after that, next time when it tries to fetch the value, it will get the new updated value and it will fetch the events after 54 or 54 onwards, right? So this is a very basic and important thing through which you'll get very good clarity. When I first understood this, oh, I felt so good. I felt okay, this is how things work, right? It makes total sense. Like, you have different offsets, and that's why all the systems, all the consumer groups are independent of each other. And that's why Kafka is so powerful. You can just imagine there are so many different consumers out there, and they can consume at their own speed, whatever time frame, independent of each other. And because there is like retention period, Kafka is durable, so the event would stay out there for so much time. So your system can fail for so many times till you feel like data is durable, data remains there. It's not like data will be lost if you're not able to process it now. So this retention period is enough time. The event will stay there for like so much time, and even if your system keeps on failing for so many days, once it is successful properly, it can consume those events and perform the task and then update the offset. Now, because I've mentioned it multiple times that consumers will consume the events, now that we know that there is offset, that's fine. But one question still comes into mind, and that is, how do consumers consume events from Kafka? Like, is it the observer pattern that the events get pushed to the consumers by Kafka, or how does that work? The answer is polling based model. So it's not like that the Kafka will push the events to the consumer. Okay, say for example, these three are the consumer groups. Okay, and they consume the events from this particular partition. Okay, and a new event comes here. So it's not like the Kafka will push this to all the consumer groups. No, that's not the case. Because if we follow this kind of approach, then it is not scalable, because you have to push to so many consumers. There can be a lot of consumers who want to consume that particular topic, the event which is part of that particular topic, right? So that is not scalable. And as we said, like, these are independent of each other, so they can consume at their whatever pace they want to and whenever they require it to. That's the beauty of Kafka. These are independent. Whenever they want, they can consume it. If we make it like observer pattern, like you are pushing it, then they have to consume it at that time, right? That doesn't provide that kind of freedom or a great approach for things, right? So instead of Kafka pushing that, we follow poll based model. Okay, so the consumer groups can poll the Kafka after some interval or time. Because they have the offset, they can poll with the offset, right? And because there is a concept of offset, now they'll poll and they'll get the offset from that internal topic, and then they will fetch or consume the events from that offset onwards, right? So we use the poll based model. So we do polling. So the consumer groups pull the data from the Kafka, and it's not a push based model. Okay, now let's try to understand this with a technical example. Okay, so say we are talking about YouTube. For complete system design for YouTube, you can refer to this video of mine where I've talked in detail about each of the component, including the use of Kafka. Okay, but I'll give you a summary. So say first, microservices upload service through which the user is able to upload the raw video to Amazon S3. Okay, and then of course we have Kafka. So let me write here Kafka. So once the work of upload service is complete, which means the raw video has been uploaded to Amazon S3, it will add an event to Kafka, and event name would be something like video uploaded. Okay, now there are many other microservices which will consume this video uploaded event. We will use transcoding service, which will basically consume this event, and its role is to convert all the different types of transcoded version like 144p, 360p, 720p, 4K, all those different resolutions you can imagine. That happens through the transcoding service. So the transcoding service will listen to this video uploaded. Okay, so let me draw an arrow here. So the transcoding service is acting as a consumer. This upload service acts as a producer because it is producing this event. This transcoding service is consuming that event. Now, apart from transcoding service, there are few more microservices which would basically consume the same event. Okay, like for example, you would have like copyright check service, which will basically check if there are any copyright issues related to the video which has been uploaded by the end user. Similarly, we will have like analytics service and much more. Okay, this is just a brief. Of course, for complete details you can refer to this video, but I'm just telling you, like, there are so many different consumers here, right? And because these are different microservices, so these are different consumer groups, and hence all of these can consume from a particular partition because these are separate consumer groups, right? So these are the consumers of the event, and this is the publisher, and in Kafka we will have the event. Okay, so when we simply use Kafka in our model, we don't talk much about the things like topic, partition, broker, offset, all such things. We simply say this is the event which is pushed to Kafka and these are the consumers, right? Because we don't want to go in detail as we are designing some other system. We are talking about YouTube. We are not talking in particular about Kafka, right? But here in this video, as we are discussing about Kafka in detail, so we have discussed some of the things like what is a topic, what is a partition, what is a broker, where are the actual events stored, and how multiple consumers are able to consume the same event. Right now we know that it is using the offset, so there can be something like the transcoding service for that particular partition can have the offset as like 112, right, which is, as I told you, per partition per consumer groups, right? And that's why the copyright service can have a different offset, like it can have like 57, right? Analytics service can have a different offset, like you can say 71, right? So they can have different offsets, so which makes them work independently. They can consume events independent of each other, right? And how do they consume the event? They poll it from the Kafka. Kafka does not push the events. They will poll the events after certain interval. You can just imagine like you have put like threshold like after every 500 millisecond, or you can say after every 5 seconds, whatever is the time limit that you have set. After that, this microservice acting as the consumer group, it will consume the event from Kafka with this offset number. Like the events after this offset number, it will fetch from the Kafka, right? So this would give you more technical clarity how things actually work, right? Okay, now again coming back to the basics related to Kafka, we saw in technical terms about like topic and partition. Let's also discuss about broker. So what is a broker? Broker, you can simply imagine as a server or a machine that stores data and serves the read and write request. So inside a broker, you would have like multiple partitions in which the actual event will be stored. Okay, so this is the complete machine which acts as like the broker, and inside broker you have multiple partitions, right? And as we discussed earlier, in Kafka you have multiple brokers. It's not like you have only one broker, you have many brokers, and combined that is Kafka. Why do we have multiple brokers? To avoid single point of failure. And overall, all these brokers combined are called as cluster, and basically Kafka scales by adding brokers, right? And overall, if you imagine Kafka, it is like a distributed log file in which you basically append the events at the end of the file, you can say. So we don't perform like update or delete operations in Kafka. We simply append at the end of the file, and this is like distributed log file. Now, as I mentioned that we don't perform update or delete operations in Kafka, we simply append at the end. So one question may come into your mind, like what if wrong data goes into Kafka? How do we handle that? Because we don't perform update or delete operations in Kafka. Basically the answer is, as I told you earlier, Kafka acts as an event stream. So inside Kafka we put the events. Okay, we don't put the messages or states. So we put events, and generally events are like something which does not contain state. Like for example, if we talk about the state of a order, it can be in the shipped state, it can be in the delivered state, it can be in the cancelled state, it can be in the returned state, right? So the state keeps on changing, and if you keep the data related to state, then you need to perform updates. But in Kafka, our data is the events. So we need to understand Kafka is not a database. Kafka is a distributed log file. Okay. But of course, there can be a case that wrong events have been inserted in Kafka. So how do we deal with it? So there are few strategies that we can discuss about. Okay. The first strategy is, in case some wrong event has been inserted in Kafka. Now, because we cannot delete or update it, what we can do is like, we can add a new event that corrects it. For example, the wrong event can be something like this. It contains some of the information like order ID, status, and in case the status is not correct, we can send another event which is correct. Okay. It will have some more information, and again, we have the status as cancelled now. Okay. And then you process this and things will be fine. Okay. The second strategy is that you validate before produce the event, right? If you validate before pushing it to Kafka, there is high probability that bad events will never enter the Kafka, correct? So you can perform the common validations like schema validation, check the required fields are there or not in the event. You can do the type checks and much more. Okay. So it's kind of like you validate before pushing the event to Kafka. Okay, then the strategy 3, which is dead letter queue or DLQ. Just in case, even after validation, you have pushed the wrong event and the consumer cannot process that message, what we will do is like, we will put that into the DLQ topic, which is dead letter queue, because your event is not correct and it is useless as the consumers are not able to consume that event. Okay, so it's kind of a state like you have malformed events, and for that you have like dead letter queue. So dead letter queue will store the malformed data, unexpected values, poison messages, and what it can do later is inspect, fix logic, and replay if needed. Now again, you don't need to remember all of this. I just told you so that in case you have questions related to this, it should be cleared, right? So just for curiosity, I told you, you don't need to remember this. But one thing that you need to remember is that in Kafka, we only perform the append operation at the end of the file. We do not perform update or delete operations. So that's why it's important to remember Kafka is not a database. Okay. Although there is some retention period in Kafka, which provides durability, but still it is not a database. So you cannot use Kafka for your CRUD operations like create, read, update, delete, because you do not perform update and delete in Kafka. Okay. So as we mentioned, we don't perform the delete operation in Kafka. Like then there will be a lot of events and then the events will keep on adding only. How can we manage that kind of system? Because all the events will keep on increasing and you're never deleting. How is that working? So the answer of that is we do not perform delete operation, but we do have retention period, right? That we discussed earlier. So say the retention period is like 28 days. Okay. So after 28 days, automatically that event will be removed from Kafka. Okay. So you are not performing any manual deletion operation. That event is automatically removed. You can treat it as like expiry of that event. Okay. So whatever the retention period is there, after that, the event will be removed automatically from Kafka. So it's not like the data keeps on increasing, because the old data, like after this retention period, that also will get removed. Okay. So it's not like it's always in the increasing state of data, right? Now one question may come into your mind here, like these are consumers, correct? So can they consume some other event as well? Yes, totally. Basically, a consumer can subscribe to multiple topics. Okay. And hence the consumer can also consume from multiple partitions. Here, when we are talking about video uploaded event, right? So how this works is like, say for example, we have multiple partitions, correct? So in this event, you would have some more data as well, right? For example, it will have like the video ID, like which video have you uploaded, and much more information can be there. But video ID is something through which we will get the partition ID as well. Because as I told you earlier, from the particular ID, we will perform the hashing function, and through that we will get the partition as well. So say this is part of this partition, right? And now all of these are consuming the events. So all of these are basically consuming from this partition. Okay. So multiple consumers from different consumer groups, that is an important point, can consume from the same partition. And another important point here is like, here transcoding service is acting as a consumer. Okay. but it can also produce an event. Okay, so it's not like if some microservice is a consumer, it cannot produce. It can say it is consuming video uploaded event, later it can produce event like video transcoded, which will be further consumed by some other consumers. Okay, because each of the microservice has its own role, and the role of Kafka here is to make overall system scalable and to remove the tight coupling. Say in case Kafka was not present here, then these microservices would have to interact with each other, correct? So it would have been the responsibility of upload service to tell transcoding service, copyright service, analytics service that okay, the video has been uploaded, right? But you can imagine that increases so much responsibility on particular microservice, because when you try to update some microservice, that can fail, correct? But now it's the responsibility of this microservice to update the other microservice. Then it becomes a lot of responsibility of upload service. Kafka acts as a wonderful component here through which you can scale the overall system and remove the tight coupling. So now you can see upload service do not need to interact with the transcoding service or this one, right? It will simply push the event to Kafka and its role is done. The consumers will consume the event by themselves. So it reduces the responsibility of upload service. Similar is the case for transcoding service. Once it has consumed the event and it has performed its action, like its work was to transcode video file into different transcoded versions like 144p, 360p, 4K, right? So once it has performed its task, it will simply push the event like video transcoded, and it will pass some information in it like what was the video ID and anything else that is required. But once it has pushed that to Kafka, its role is done. Whosoever wants to consume that event, that's their responsibility, not transcoding service responsibility, right? So that's why Kafka is really important. Okay, and the main point I wanted to tell here was consumers from different consumer groups can consume the event from the same partition, and a consumer can also be a producer for some other event. Okay, so we mentioned earlier in this video that for each of the partition we will also have the replicas, right? So let's discuss about it in detail. So here you can see is an example of creating a topic, right? So first we write create and then we give the topic name for the property topic, and then we provide the partitions count for the property partitions, and then we also mention the replication factor, right? For example, we have mentioned 3 here. So this means apart from the original one, we will create 2 more replicas. So overall we have 3 copies, right? Now to take an example, let's reduce the size. Say we make partitions as 3 and the replication factor we keep it as 2. Okay, so if there are 3 partitions, say we have like P0, P1 and P2. So we have 3 partitions. Now what does these partition represent? As we have already discussed in a topic, we can have multiple partitions, and the role of partition is to provide parallelism so that there can be multiple reads and writes happening. And there are much more benefits of it, right? Like we discussed earlier in this video, the role of partition, correct? But now another point is to avoid single point of failure. Okay, because we have this replication factor. Now here we have kept the replication factor as 2, which means apart from this we will create 1 more replica, so that overall there are kind of 2 copies, correct? And why do we need that? Because just in case say P0 is not working or crashed or anything like that, right? So if partition 0 is not working, then it would act as single point of failure, right? So to avoid the single point of failure, we have this replication factor, so that in case P0 is not working, the replica can be used. Okay, so let's see for this example. Now that we have replicas, like for P0 we have 2 things, this one and this one. So the question comes, from where read and write will happen? The answer of that is we use leader follower model in Kafka. Okay, now what this means is, say for example we have these 2 partitions, because the replication factor was 2, so we have original one and 1 more copy, correct? So overall we have 2, correct? So these will be present in different brokers, correct, to avoid single point of failure properly, because just in case both of these, even the replica is present in the same broker, and say the broker dies, that is the machine or the server in which partition exists, if that dies, again you will fall into single point of failure because both of these will stop working, correct? So these will be part of different brokers. Now let's say this is part of broker 0 and this is part of like broker 1, correct? So this leader follower pattern is that we will assign one leader broker for the partition and the other one would be the follower broker for that particular partition. Okay, so say we choose broker 0 as the leader for this partition P0. Okay, so this will be follower. Okay, so this is leader, this is follower. So all the reads and writes for partition 0 will happen from this broker, and this broker which is acting as follower will just keep on replicating the things. Both of these will have totally same things. Okay, all the events will be same, even the offsets of those events which are present in this partition, that will also be same for here. Okay, so it's kind of complete replica, but reads and writes are not happening from the follower. Reads and writes are happening only through the leader, and the use case of follower here is just in case the leader goes down or is not working properly, so you don't want that to act as single point of failure. So in that case, the one of the followers, now because here we had only one follower, so the follower will act as the new leader. So the follower will be assigned the role of new leader. Okay, so that's a use of replica. So for this case where replication factor is 2, we would have something like this, correct? So because we mentioned number of partitions as 3, so like P0, P1, P2, we will have like partition 0, partition 1, partition 2. But after that, we also mentioned the replication factor as 2. So there will be one more copy, correct? For each of the partition. When we say replication factor, that is applicable to all of the partitions. So here that will be applicable to P0, P1, P2. So all of these will have one more copy. So as I said earlier, the replicas would be generally present in some other broker, correct? A broker can contain multiple partitions, right? But what we want here is that the replica should be in different broker so that we are handling single point of failure. Okay, so here you can see for partition 0, one is present in one machine and another copy would be present in some other machine. Similarly for partition 1 and partition 2. Okay, and one of the broker will be assigned as the leader broker, from which all of the reads and writes will happen for partition 0, and all of the others will be assigned as follower, because here we had just one more copy, so that will be assigned follower. If you had like say 4 copies, 5 more copies, all of those will be assigned as a follower. So clearly you can see only one of the broker will be assigned as leader and other will be assigned as follower. Okay, and only leader handles reads and writes. Okay, what's the role of followers? Followers will replicate the data and one of the follower will take over in case the leader fails. Now here the main part is, don't confuse the replication factors, replicas or the leader follower with the partitions. Okay, for each topic there can be multiple partitions just like we discussed, and that's a very important thing, and that is how we follow the scalability and parallelism and much more in Kafka. Replication factor is just additional thing to avoid single point of failure. Okay, so don't confuse the replication factor with the actual partitions. Okay, so the replication factor is just like in system design we always say that we have to reduce the risk, we have to avoid single point of failure. For that we have this replicas. Like that happens for all of the components. Even in databases we have like multiple replicas to avoid single point of failure. There also we have like master slave architecture, and when we talk about servers also, there are set of powerful machines. It's never like one machine. Okay, so that's a basic concept. Like replica is a basic concept of system design, because we are designing for complex or big systems, so we need to keep in mind of these replicas to avoid single point of failure, but don't confuse these with the actual partitions. Okay, so one question that may come into your mind is like we said like follower will replicate from the leader, correct? But here we know that follower is some other broker and leader is some other broker. So how is follower replicating the data from the leader? So in this case also we use the pull based approach. Okay, so the follower will pull the data from the leader. Okay, very similar to what consumers do to fetch events from the partition, they poll, right? And similarly here the follower will also poll to replicate the data from leader, and they do after some particular intervals. So of course there can be some lag between the leader and the follower. But if we ignore that, overall the follower will be the complete replica of the leader. All the events and even the offsets would be same because it is a replica, correct? Again, don't confuse the replicas with the original partitions, because as you remember, like all these partitions are part of this topic, right? And these are independent of each other, whereas when we talk about replica, say when we are talking about partition 0, so these will be exactly kind of same because these are replicas, just to avoid single point of failure. Now because we are talking about replicas here, one basic question may come into your mind: how many replicas do we usually keep for partitions? So basically replication factor as 1 is kept for like development or testing purposes, 2 kept for small internal systems, replication factor as 3 is generally the industry standard, and 4 plus is used for very critical systems. Okay, so generally we will pick 3 as a size in case we are designing some big system. Okay, now that we have mentioned that there are replicas and we follow the leader follower pattern, so for a partition, one of the brokers will be assigned as the leader and other will be assigned as the follower. So the question that comes into mind is, how does Kafka know which broker is the leader for a partition? So answer of this is using the Kafka metadata, and this metadata is managed by the Kafka controller. Alright, so I've mentioned here like all this information will be part of the metadata, which is handled by the Kafka controller. You don't need to remember all of this. I'm just telling you so that in case you have such doubts in mind, it gives you clarity, or when you think in this way, it makes topic more interesting. Okay, so don't worry, you don't need to remember all of this information. Just listen this and maybe enjoy the interesting facts related to a system design component. So basically Kafka maintains the metadata, which will contain a lot of information like the topic list, all the partitions related to topics, and then for each of the partition it will contain the information like the leader broker and replica brokers, and there will be much more information as well. Okay, and this metadata is stored in the Kafka cluster and it is managed by the Kafka controller as I have written here. Okay, now through this metadata everyone gets clarity like where should the request go to, because as I said, all the reads and writes should happen from the leader broker of the partition, correct? So we should know the leader, correct? And we get that information through this metadata. And when we talk about Kafka controller, in older Kafka systems, Zookeeper was used to play this role, correct? But in new Kafka, system like Kraft is used as a Kafka controller. So basically when a topic is created, alongside that, as we saw, like partitions will be created and then the replicas will also be created. Then Kafka will decide which brokers will host the partitions, because there are multiple partitions, correct? And then we also have replicas for each of the partition, and we want to keep the replicas in different brokers to avoid single point of failure. And even in a single broker you can have multiple partitions. So basically Kafka will decide which broker will host the partitions, which broker is leader, and which are the followers. Okay, so overall Kafka handles it so that there is evenly distribution and no broker is overloaded. And why Kafka is doing that? So that there is even distribution, no broker is overloaded, and replicas are on different machines. So for example, it would be something like this. For partition 0, the leader broker is B1, follower is B2. For partition 1, the leader broker is B2, follower is B3. Partition 2, leader is B3, follower is B1. Now here it does not mean it will be sequential. It is just an example. Any broker can be chosen, okay, and that decision is done by Kafka. So it can also be like partition 0, it can make leader as B4, correct? So it can be anything based on even distribution, it can basically decide. Now because we have talked about Kafka metadata here, so one question that may come into your mind is like, how does Kafka metadata look like? So Kafka metadata is basically a routing table. So as you can see here, this is kind of structure. So as we know, Kafka cluster means inside which we have multiple brokers, correct? So it will have brokers, and for each broker ID we will maintain host and the port. So here you can see we have the list of topics. So for each of the topic name we will have the partitions, and because there can be multiple partitions, so we have list of partition, and for each of the partitions, say P0, we maintain like the leader broker, replicas, and much more information. ISR basically represents here like how many followers are in sync with the leader. Okay, so don't worry about it. but overall you can clearly see it contains all this information. Now this was kind of a structure. Let me also show you proper example for this. So this is an example of this structure. Okay, so it will contain orders related events, correct? Inside this we have two partitions, partition 0 and partition 1, and because each of the partition has a replica and we follow the leader follower pattern, so each of the partition will have a leader broker. Say for example broker 1 is assigned the leader broker, and then there are replicas as well. Okay, and similarly for partition 1 we have the similar information. So kind of this is the metadata, and this is maintained by Kafka controller. Now from the metadata actually the complete system will get to know, like for each of the partition, which broker is the leader, correct? Because from there only reads and writes will happen for that partition, correct? And now another thing is, even the consumers and producers will get to know from where to write or read using this Kafka metadata only. Okay, because otherwise producer won't know where to write or consumer won't know where to read from, right? And that detail we get from this metadata only, because it clearly tells for this topic we have these partitions, correct? And for this partition this is the leader broker. Now as I mentioned that even the consumers and producers will use this metadata, so it takes us to a very interesting point, like what is the complete end-to-end Kafka flow. Let's try to understand that. So basically the step 1 is where producer wants to basically send the event, but the producer does not blindly send the events or data. First step is basically the producer will connect to any of the broker, because till now it does not know who is the leader, who is the follower. It will just randomly connect to any of the broker. Say it connected with broker X, correct? And it will ask give me cluster metadata. Now the step 2 is that producer will get the metadata. Metadata, as we saw, is handled or managed by the Kafka controller, right? So once the producer receives the metadata, now producer knows all the brokers, all the topics, all the partitions which are part of particular topic, and for each of the partition it will get to know which one is the leader broker. And because this information does not change very frequently, so the producer will cache this information. Now next the producer wants to send an event as a step 3, correct? So now producer has already received the metadata and it has all this information, so it just wants to send an event now. So although it has all this information, producer still needs to identify which partition should this event go to. Okay, and the interesting part here is that this is producer's responsibility. This is not the responsibility of Kafka. Okay, this is producer's responsibility. Let me try to explain it to you in case it is becoming confusing. Okay, so as we said, like there can be multiple topics. For example, this is football events and this is one of the topic. Now inside this topic we mentioned like there can be multiple partitions. P0 can be there, then there can be P1 as well, then there can be P2 as well, right? So these will be present in different brokers, correct? And these will be handling different matches, correct? So P0 might be handling like match 0 and then match 3 as well, right? Whereas this P1 might be handling like match 1 and match 4, right? So these are handling different matches, correct? So the producer who wants to send an event, it needs to identify to which of the partition this event should go to, because it now knows the topic, correct? Because based on the event it already knows the topic, but it does not know which partition it should go to. But the point is to identify this is the producer's responsibility, not the Kafka's. So with this we come to step 4 where the producer chooses the partition. How does it choose? As we already discussed earlier, like partition 0 is handling match 0, match 3. How is it handling that? Based on the key. So basically match 0 will have a unique ID, correct? And similarly match 3 has unique ID, and through that ID we can clearly identify the match, correct? Now based on this ID we can also calculate the partition, because we can simply have a hash function through which we can get the partition based on the ID, right? So if we take the case where the key or the ID is present with us, then in that case the producer can simply identify the partition by this. So basically it is doing like hashing function, and then we are doing modulus number of partitions, because number of partition it already knows now using this metadata, because it gives like all the partitions for a particular topic, correct? So we will have the number of partitions, and producer will also have the hash function. This hash function is also provided by Kafka. Producer just needs to apply this kind of logic to identify the partition, so that overall responsibility of Kafka should reduce. This can be handled by the producer itself. Okay, so simply applying the hashing modulus number of partitions, producer will get the partition. For example, the order ID is 123, so we will put the 123, the order ID, inside some hash function. Say we got some value from it, say we got value 4 from this hash function, and then we do modulus 3, then it will return partition 1, because 4 modulus 3 gives you 1, right? So it is kind of like if the order ID is 123, always you will go to partition 1, right? So using this way, basically the producer can also identify which partition it should go to. Okay, now it knows the partition ID, and based on the metadata it also knows for the partition 1 which is the leader broker. So it can basically identify now all that stuff, and it can directly send that event to that particular leader broker of partition 1, right? The good part here is the same key would always provide the same partition, because we are simply applying hash function and then modulus number of partitions. And that is why also we talked like ordering is preserved in a particular partition. Across partitions it is not maintained, but in a partition it is always maintained. Now this was a case when key is present, and generally this will be the case when you require ordering, correct? Say for example, whenever you're talking about a particular match, so you have the match ID that acts as a key, right? And using this strategy, you know the partition, and hence the ordering is also maintained. But just in case key is not present, then we simply follow the round robin approach, because we don't care about the ordering then, right? If ordering matters to us, then we would simply use a key. Okay, so the case 2 would be you simply do the round robin and pick the partition of that particular topic, and once you pick the partition, then of course from this metadata you'll get to know which is the leader broker for that partition. So next steps, as I mentioned, basically the producer will find the leader broker from the metadata. Like for example, for partition 1, from the metadata it will get the leader broker is 2, and then producer sends the event directly to broker 2. Okay, so in this way we don't need any load balancer and we don't need any proxy. So using the metadata we get all the information, and basically we apply this logic on the producer itself. Then the next step is the leader broker writes down, because from the producer you got the event on the leader broker, and now the leader broker writes the data. So basically the leader broker of the partition will simply append the record to the partition log, and it will assign the offset, because as we discussed earlier, offset is something which is assigned by Kafka itself. It is internal to Kafka, right? So once we have appended a record, we will assign it an offset, because every event has an offset, right? And then we will start the replication to the followers. So after this, the next steps are like followers will replicate. As we discussed, like followers will pull the data from the leader, right? So followers will pull data from the leader, and then the followers will append those events to their own logs. Okay, and then they will also send the acknowledgement, and based on the acknowledgement, leader can update this ISR that we saw in the metadata and also acknowledge the producer. Okay, so these all 7 steps were the process, like how producer will write the event to Kafka. Like it needs to identify the partition, correct? That it will identify using this logic, and once it knows the partition of a topic, then basically it will identify the leader broker using that metadata, and once it has all that information, it will simply write that event to that particular leader broker of the partition, and then of course replicas will replicate the data from the leader. Okay, so this was producer flow. And then when we talk about the consumer side flow, the consumers will also get the metadata. Okay, in case you need to consume the event, so you should also know like from where to read the data. For that also consumers get this metadata, very similar to how like producer got it, and from the partition they will get the leader from that metadata only, and then they will simply pull the data and track the offsets. So quite similar approach to what we discussed for the producer. Okay, So this is the overall flow, how basically writes and reads happen to Kafka. Okay, again, you don't need to remember all of this flow, but it is quite interesting, right? So that's why I thought I should discuss it with you, right? So here one interesting point was that this logic to identify the partition is the responsibility of the producer, okay, and not Kafka. Now with this, we have covered most of the concepts related to Kafka, but I know there might be a lot of questions in your mind. So now let's discuss some of the common questions that may come into your mind related to Kafka, okay? So one question could be, why is ordering guaranteed in a partition but not across the partitions? So to answer that, basically as we discussed, you can imagine partition as a single log file, okay, and we append only at the end of the file, right? And we also said like partition will be present inside a broker, okay? So let's imagine this is broker 1. Broker simply means the server or a machine, okay? And this is broker 2, okay? So for a topic, you have multiple partitions. One of the partition of that topic is present in this broker. So P0 is present in broker 1, and partition 1 related to the same topic is present in broker 2. And similarly, there can be many more partitions which are present in different brokers. Now why these partitions which are related to same topic present in different brokers? In order to avoid single point of failure, just in case all of the partitions were present in the same broker, and if that machine or server or that broker goes down, then all of the partitions will go down, right? And we don't want that. So in order to avoid single point of failure, our partitions which are related to same topic are distributed in different brokers, right? So now let's say for this partition, first A event came and after that C event came, okay? And for partition 1, B event came and then D event came. Now you can clearly imagine here both partition 0 and partition 1 are independent of each other, right? They are handling different kind of data. Like for example, in the sports case that we discussed, P0 might be handling match 0, match 3, whereas P1 might be handling match 1, match 4. So they are handling different events. That's why they are independent, correct? And that's how we increase the scalability and parallelism in Kafka, correct? So now here you can clearly imagine like partition 0 knows that A came before C, correct? And partition 1 knows B came before D. So order within a partition is clearly maintained. But there is no way that partition 0 would know that B came before C or after C, or even before A or after A, correct? Because these two partitions are kind of independent of each other. They are operating independently, and that's why we are getting scalability parallelism. In case we have to maintain order across the partitions, then you have to maintain it globally, and that is not feasible. Then overall all the scalability factors and parallelism factors, they might not work that well. Okay, so that's why ordering is guaranteed within a partition but not across. And the good part is when we say the ordering is maintained within a partition, that really helps, because if you pass some ID in the event, through that we can always put the event related to some particular ID in the same partition. So for example, if we are talking about match 1 related to FIFA, so all of the events related to match 1 will always go to partition 0, because the match ID will be same for all of those events, right? And we will maintain the order as all of those events are going to same partition, correct? And when we talk about different partitions, they might be present in different brokers. So clearly the machines are different. So if they need to interact, that would happen using the network calls, which are slow. And even there are parallel writes happening to both of the partitions. So if we need to coordinate, then overall the complete system will become slow. And that's why ordering is not guaranteed when we talk about across the partitions in Kafka. Okay, now let's move to the next question. Okay, another question can be, can multiple consumers read from the same partition at the same time? So it totally depends. See, if we are talking about one consumer group, so say this is a consumer group and these are the multiple consumers here. So we have like C1, we have C2 and we have C3. So 3 consumers are present in a consumer group. And say we are talking about a partition, say partition 0. Okay, so can C1 and C2 both read from partition 0? The answer is no. Why? Because only one consumer from a consumer group can consume events from a partition. If C1 is consuming from partition 0, C2 cannot, because that would cause order and offset related issues. Like we discussed earlier, say there are 3 employees in a company. So you don't want multiple employees to focus on same match, right? We want each of the employee to be most productive, right? So they will focus on different matches, different partitions. So here also in a consumer group, only one consumer can consume from a partition. But if we talk about different consumer groups, like here, if C1 is part of say consumer group 1, okay, and C2, this one, is part of some other consumer group. So let's put this CG2, right? And let's also make C3. Now C3 is also part of some other consumer group, CG3. Okay. Now because all of these consumers are part of different consumer groups, so now it is totally fine if these consumers consume from the same partition. Okay, because these are part of different consumer groups. So now this is totally fine. So the rule is only one consumer can consume from a particular partition from a consumer group, but consumers from different consumer groups can consume from the same partition. Okay, so this is not allowed and this is allowed. Another thing is, like, a consumer can also consume from multiple partitions. It can subscribe to multiple topics as well. So here, if consumer 1 is consuming from partition 0, it can also consume from some other partition, say P3. Okay, so it can consume from multiple places, and that's the beauty of Kafka, the event stream. You can have multiple consumers. In message queue, you can have only one consumer, but in event stream, you can have multiple consumers, right? Now, how is this being possible that from partition 0 different consumers are able to consume? That is possible due to offsets, right? Because offset is per partition per consumer group. All of these have different offsets, and that's why they can operate independently. So this is one of the examples. Say for example, we have a topic T, and for that topic T we have 3 partitions, P0, P1 and P2. Now let's say there are 2 consumer groups, G1 and G2. Inside G1, we have 3 consumers, C1, C2, C3, and inside consumer group G2, we have again 3 consumers, C4, C5, C6. Okay. So here you can see for a particular partition, not more than one consumer from the same consumer group can consume. Okay. There can be only one consumer per consumer group to a partition. So say C1 is consuming from P0, C2 is consuming from P1, and C3 is consuming from P2. So clearly you can see there is parallelism, multiple writes, multiple reads happening due to Kafka, correct? So if there were 3 employees, each of the employee has been assigned some task, so they can operate independently. And similarly, when we talk about consumer group G2, one consumer is consuming P0, then another P1, and then another P2. So the golden rule, only one consumer per consumer group can consume a particular partition. But clearly you can see a partition can be consumed by multiple consumers which are part of different consumer groups. For example, here P0 is consumed by C1 as well, and C4 as well. Similarly for other partitions as well, and that we saw here as well. Like P0 is consumed by C1, C2, C3. Why? Because C1, C2, C3 are part of different consumer groups. Alright, now let's move to the next question. And the question is, as we discussed earlier, that you need to provide the number of partitions while defining the topic. So the question is, how many partitions should we choose at the beginning? So for example, if we see here, while creating the topic, we define the number of partitions, correct? So this can depend basically on few factors, like what is the expected throughput, like what are the number of events that you expect per second, and also you need to think about like what are the maximum number of consumers that you will ever need, because through partitions you do parallelism, like parallel reads, parallel writes, and it helps in scalability. But it also depends like how many consumers do you have, because those consumers will consume from the partition, right? So it depends on that as well. And then another factor is broker capacity, which means the capacity of the server and the future growth that you can think about. But normally what we can say is like if the system is small, then 3 to 6 partitions are enough. If we have medium level system, then 12 to 24 partitions, and if we have the large system, then 50 plus partitions can be assigned. Again, you don't need to remember this, but I just told you in case you have some doubt like this. Now that we need to define the partitions at the beginning, so one question may come into your mind, which is, as we have defined the partitions in the beginning, what if events become huge later? Can we increase the partitions? The answer is yes, you can increase the partitions, but there can be issues due to it. Because as we said, like partition maintains the order of the events, right? So like for example, for P0, if we are talking about the sports related topic, like the FIFA events is the topic, and for match 0 and match 3, all the events were going to partition 0. Okay, say we had like 3 partitions, and for match 1 and match 4 it was going to P1, and then match 2 and match 5, those were going to P2. Okay, how is that going? Because each of the event would say contain the match ID. Okay, and after getting the match ID, we will apply the hashing function through which we'll get the partition. So because the match ID is consistent for a particular match, all of the events we're going to say P0 when we are talking about match 0, right? Now let's imagine that you have made your mind to increase the partitions, right? So now you have introduced P4 as well, and your hashing function was say something something, and then you do the modulus of number of partitions. So earlier you used to do modulus 3 because there were 3 partitions, P0, P1, P2, but now because you have introduced a new partition, so your hash function might change. It would be whatever you were doing and then modulus number of partitions, which now become 4, correct? And now you can imagine it can happen that for a particular match like M1, and now you can imagine the events which were going for match 3 to P0 now may go to P4, correct? Because your hash function has changed, right? So increasing partitions come with an issue that ordering might not be maintained now. Okay, now does this issue even come when one of the partitions is down? Like for example, ignore the case of P4, we had 3 partitions, P0, P1, P2, okay, for a particular topic, and now let's say P1 goes down. So does this problem come in that case only? The answer is no. Why? Because as we discussed earlier, for each of the partition we will have the replica partitions as well. You have that replication factor, right? So say for example here it is 3, so we have 3 copies for each of the partition. So in case any of the leader partition is down, one of the replicas is made the leader partition. So total number of partitions will still remain the same, because instead of P1 we will use the replica of P1 and assign it as a leader. So hence you will again have 3 partitions, so your hashing function remains the same. Okay, again, I mean, the most of the questions that I am discussing here, you don't need to remember that. Okay, I'm just telling you so that you get more clarity about Kafka. Okay, the important parts are related to the offset and some of the basic understanding that consumers pull from Kafka and they use offset. Okay, so all those basic things are good to understand. These things are just like additional points that I'm telling you. So don't worry like you have to remember everything. It's not like that. These are just kind of interesting facts, or out of curiosity, if you want to know, these are good things to learn about Kafka. It makes things more interesting. Now let's go to the next question. And the question is, when are events deleted from Kafka? So as we discussed earlier, in Kafka, we only do the append operation at the end of file. We do not perform update or delete operation. And also, as Kafka acts most of the time as event stream, it does not delete the messages after consumption. Okay, so it's not the case like you had an event in Kafka and then all of the consumers from different consumer groups consumed that event. Okay, so it's not like after the consumption that event will be removed from Kafka. No, in case of message queue, what happens is there is only one consumer, and once the consumer consumes that message is removed from the message queue, but not in case of Kafka, which acts as event stream. So here the events are deleted based on retention period, like what is the time, like that is set via retention.ms, and retention size, and the property is retention.bytes. So for example, the retention time is set as like 21 days. Okay, so after 21 days automatically the event will be removed from Kafka, and this will be irrespective of the fact whether consumers have consumed the event or not. Even if not a single consumer has consumed the event, after this retention period, that event will be removed from Kafka. Okay, so based on time and size, whatever reaches first, the event is deleted based on that retention criteria. Okay, so even if you remember like retention period or retention time, that is more than enough. Like you can simply remember that this retention period provides durability factor in Kafka, so that even some of the consumers have failed to consume the message, they can consume it later because the event will stay till the time of this retention period, right? So this retention period can be few days, like you can imagine like 7 days or even longer, like 28 days. So few days you can imagine, and it can go like few weeks, like as I said, like 28 days would become like 4 weeks, right? But Kafka is not like persistent storage. Okay, in database you have persistent storage, like your data can stay there for years, right? And database is used for CRUD operations as well. So even if the data keeps on changing, you update that, you can also delete that. So Kafka is not a database because first of all, the storage is not like for years or something. Just for the durability factor, it is for few days, and also we don't perform update and delete operation in Kafka. Okay, now let's move to the next question. And the question is, what are the different offset commit strategies in Kafka? And what are the different delivery guarantees, like at most once, at least once, or exactly once in Kafka? And which one of these is the default one in Kafka? So basically, as we mentioned that multiple consumers from different consumer groups can consume from the same partition using the offset, right? And now how do we commit the offset? Say you have consumed some of the events, and after that, how do we commit the offset? Based on that, we will have different delivery guarantee. Like for example, the first offset commit strategy is auto commit, which means that Kafka automatically commits the offset periodically. Now this approach is quite risky because, say for example, this consumer had offset of like 30, okay, and now it consumed the events from 30 to 40. Now while it was processing those events, and Kafka did the auto commit to 40 for this consumer group, okay, and what can happen is that we have already made the commit of offset, but this consumer group can crash right before completing its task. It can crash because it's just a system, right? So in that case, what will happen is, because this system has not performed its complete work, it will again try to fetch the offset from Kafka when it is totally up. But now instead of 30, it will get the offset as 40, correct? Because Kafka did the auto commit on the offset, assuming that the system has already picked it, so we can do the auto commit. But there can be this kind of failure scenario, and that's why this approach is risky. So in this example, the events from offset 30 to 40 will be lost because we have already updated the offset, but while executing that, the system had crashed. Now because we saw some of the issues around this is risky, so it is not recommended to use this auto commit strategy. Okay, so the next offset commit strategy is manual commit, which is recommended, which means instead of doing the auto commit, we will do the manual commit. Now it can be of two types, synchronous, asynchronous. We'll see that case, but it is something like once you have processed the message, you are then committing the offset. Okay, now next, if we talk about delivery guarantees, there can be three kind of delivery guarantees: at most once, at least once, and exactly once. Let's try to understand all of these. At most once means that the event can be processed maximum one time. And how can that happen? Let's try to imagine an example. So say the offset for this partition and consumer group was 17. Okay, now this consumer group tries to fetch the events. Okay, so say it fetches the event from 17 to 24. Okay, but before performing its task, okay, we update the offset. So as soon as it fetches the events, we update the offset to say 24. Okay, now what can happen is, like, either this would be successful, then it's totally fine, but there can be a situation that this can fail as well. Like it got the events, but while processing those events, it got crashed, right? So it won't be able to successfully perform the actions related to 17 to 24 number offset events, correct? But we have already updated the offset number here, because as soon as you pick the events, we have updated the offset. So next time when it tries to fetch, it will get like 24 as the offset, and it will pick the events 24 onwards, correct? So that's why this is at most once, that you will be able to consume the events at most once, not more than one time. Okay, next delivery guarantee is at least once. And let's imagine how this will happen. This actually means that the event will be consumed at least one time. Okay, so let's see for this consumer group. Say the offset for this consumer group and partition was 5. Okay, and now it tries to fetch the events from 5 to 10, correct? And in the earlier strategy, whenever you fetch the events, we updated the offset, but here in this case we are not doing that. So it will get the events and say while processing the events it failed. Okay, so offset will not be updated, because we will update the offset only once we have completed the task, right? So say for 5 to 10 events, like this had to perform some task. Now it was performing some task, and say all of the tasks were done, but one thing remaining was to commit the offset, correct? So it had to commit, like the new offset is 10. It has performed all the tasks, but just committing part of the offset was remaining, and then it crashed. Okay, so now what will happen is it has already performed all the things. So say these all completed, but the offset committing part did not complete. Okay, so in that case, next time when this system is up, again it will ask from Kafka the offset, and it will get 5 again, because we have not committed the offset, right? So again it will get the events from 5 to 10, and again it will perform the task. And now in case it is still up, it can update the offset, so it will commit the offset. Instead of 5, it will become 10. So here you can see we have consumed those events twice, so more than once. So this approach is guaranteeing at least once delivery guarantee, because in this case we are committing after processing the events, right? So in at most once, as soon as we pick the events, we have committed the offset. But in at least once we have completely processed those events, then we will commit the offset. And the last category is exactly once. So in this case, we will use Kafka transaction. Okay, I have explained about transaction in database. Actually, you can refer to this video, you'll get an idea of what that means. In similar way, we have Kafka transactions. For example, in the second case, we said like it processed the actions from 5 to 10 event offsets, but before committing it to the Kafka, that offset, it failed, right? So instead of doing that, we will have like something, all of these operations will be part of one transaction. So what's the point of that is, in case you have performed some of the operations in a transaction, but before completing the last thing, okay, your system failed, then we generally roll back to the previous situation. Okay, so in case you have completed 5 to 10, but you were not able to commit the offset, but because all of these were part of single transaction, you failed in one step, which means you roll back to everything. So you go back. So whatever you did here will also be rolled back. And once your system is up again, it will again ask what is the offset. It will get 5 because you were not able to update the offset or commit the offset last time. So you'll get 5. Again, you will perform the actions. Now this is exactly once here, because whatever you did were rolled back. Okay, so you are doing that once only. And then only once you are able to perform all the things, including the commit of offset, only then the complete transaction will be successful. Okay, or you can also think in some other terms. I just gave you one reference similar to database. If you relate to database, you can think in similar terms for this. Okay, but you don't need to, keep exact idea of this. I was just giving you examples through which you can get some clarity. Okay, but we have these three as the delivery guarantees. And what is the default one in Kafka? It is at least once, which means Kafka ensures by default that the event is consumed at least once. And that's the durability thing, right? So based on which offset commit strategy do we use, the delivery guarantee will be according to that. Like we discussed about the manual commit, right? So if we are manually committing after processing the events, then it will become at least once. Because as I explained earlier, there can be a scenario that you process the events, but before committing, your system crashed. And next time when the system is up, again it will fetch the offset from the Kafka. It will the old one because we did not commit the updated offset. So again it will process the events. So clearly here we are processing the events. It can be more than one time also. But if we do the commit before processing the events, then it makes at most once. Like you fetch the events and you committed the offset, and after that you process the events. So a case can happen like while processing the events, your system is crashed, and hence those events will be lost because you have already committed the updated offset to Kafka. Now let's check the next question. How do consumers know an event has arrived? So it's important to understand that Kafka does not push events. Consumers poll the event from Kafka. So it means that consumer doesn't get notified. Basically what happens is like consumer polls the Kafka periodically. If there is no data, the broker or the server will wait, and when the data arrives, broker responds immediately. So this process is long polling. But the important thing to remember here is that there is nothing like Kafka will notify all of the consumers. No, Kafka will not notify. It's not a push-based approach. The consumers will pull the data from Kafka. And Kafka chooses pull-based approach instead of push approach for scalability. Now after this, next question is what happens during consumer crash? So let's say we are following the default strategy, which is at least once delivery. We discussed about it few minutes ago, right? So this one, at least once, which means we will commit after processing the events. This is the default delivery guarantee of Kafka, due to which we get the durability and reliability. So let's say we are following this default approach. Okay. So let's say the scenario is the last committed offset was 100 and then consumer fetched up events till 110. Now while processing it, say the consumer crashed before committing. So we have not processed the events completely, or before committing the offset, the consumer crashed. Now once the consumer is up again, so it will again fetch the offset from Kafka, which is present in the internal topic of Kafka, right? So again, it will return the offset as 100 because consumer did not commit the updated offset, right? So consumer will again start from offset 100. So this means the records or events with offset 100 to 110 are reprocessed. So there can be duplicate processing of the events, which is totally fine because we are mentioning the delivery guarantee as at least once. Okay, so what we want is like the event should be consumed at least once, and hence there can be duplicate processing. What we want is reliability and durability, that all of the events must be processed at least once. So this is the delivery guarantee that Kafka provides by default and which provides durability and reliability. So using this approach of at least once delivery guarantee, Kafka avoids data loss. So Kafka is giving preference to duplicate processing over data loss, because using this delivery guarantee, no event will be lost. So Kafka is giving priority to duplicates over data loss. Now one question would be like, how would we handle the duplicate data? So duplicate data can be handled by idempotent writes and deduplication logic. So there are strategies to handle the duplicate data. But in case you lost the data, that can never be recovered. So that's why we are giving priority by default to duplicates over the data loss. So after this, the next question is related to offsets. We discussed like using the offsets, multiple consumer groups can consume from the same partition, right? So the question is, can offsets go backwards? So generally, as we discussed, like the offsets are in the increasing order, right? For each of the event, you get an increasing number, correct? And once the consumer group consumes some events, it will commit the updated offset, which will be more than the earlier one, right? So normally the answer would be no, because offsets are append only. But Kafka also provides one feature where the consumer can manually seek for the offset. This can be done something like this. You can see we have written here consumer.seek, and inside that we have passed the partition and the offset. So using this, you will be able to check the event on particular offset, right? Why would this be required? This can be used for replay, debugging, and much more. Okay, again, I mean, you don't need to remember this. I just told just as a random interesting fact. Now, because we are talking about offsets, next question is also related to offset. So the question is, does every event have an offset, and who assigns the offset? So the answer is yes, every event has an offset. And another important point is offset is unique only within a partition. Now, what does this mean? It simply means, like, say you have these two partitions, right? These are different partitions. So say this is P0 and this is P1. Okay. So as we said, each of the event will be assigned an offset. So it can be, for example, 0, 1, 2, and it goes on, right? And similarly for P1 also you can have offset, like it's just an increasing number, right? So it can be again like 0, 1, 2 and goes on. So you can clearly see both of these have a common offset. That's totally fine. The only important thing is like offset would be unique per partition. Like in partition 0 you cannot have two events having same offset. So all the events have different offset, and that's what matter because these partitions are independent of each other. Now the question comes, who assigns the offset? Is it the producer? No, it's not the producer. It's the Kafka broker or the leader of the partition which will assign the offset. So basically producer will send a batch to partition leader, and then next step is the broker appends the records to the log, because as we said, like Kafka is actually a distributed log file. So we simply append at the end of the file, correct? And then the broker assigns offset sequentially. So it's the Kafka which is assigning the offset. It's not the producer. So now let's see an example. Say the topic is orders and the partition is P0, which the leader broker is B1. Okay, because we know that writes and reads happen from the leader only, correct? So we have mentioned that here. Okay, so now here you can see we have like offset and the event. Say the event was order created for 101 as an order ID, or then order created for 102 ID and order cancelled for 101. So all of these have been assigned a sequentially increasing offset. So 0, 1, 2, and that has been assigned by Kafka broker. So the important point is producers do not control the offsets. So producer will simply send the event. Offset is the responsibility of Kafka's broker. Okay, so the offset logic is by Kafka. There is no control of producer in it. Now where is this offset stored? It is stored in the Kafka's internal topic consumer offsets, and offset is per partition per consumer group. Now as we are talking about consumer offsets internal topic, so the question comes like, what exactly is stored in the consumer offsets topic? So basically each record in the consumer offsets topic would contain the committed offset, but it would correspond to this. We would have the consumer group ID, the topic, and the partition. As we said earlier, the offset is unique per partition per consumer group. Okay, so that's why here all this information is also stored for the committed offset. Now let's see an example. Say the group is payment service, topic is orders, partition is 0, and the committed offset is 125. So you can think of it as a map. So we have payment service, which was the consumer group, then orders, which is the topic, then the partition, which is P0, and corresponding to this key we have this value, which is the committed offset. Similarly, another entry would be the same consumer group, the same topic, but the different partition, it would have a separate value, right? Because the offset is per partition per consumer group. So this is acting as the key and this is acting as the value. So the offset is the value and this is the key, which uniquely defines offset per partition per consumer group. So after this, the next question is, what is backpressure? So let's try to understand it in a very simple way. Say we have this producer and then we have the consumer. So now the case is the producer is producing very fastly a lot of events, but consumer is consuming slowly. So we have the fast producer and slow consumer. So this is the problem statement. Now backpressure is a mechanism that prevents this problem. The problem where the producer is fast and the consumer is slow. So in Backpressure, we need to solve this problem, because if we don't solve this problem, then there can be many issues like memory fill-ups, thread blocks, JVM crash, data loss, and much more. Now Backpressure is solved by Kafka. How? So let's say I introduce Kafka here. Okay. So the fast producer can produce a lot of events, and all those events will be stored in Kafka till we reach the retention period, right? And then consumer can consume from Kafka. So even if the producer is very fast and the consumer is slow, it is totally fine. Why? Because in Kafka, we do not use push based approach. So it's not like Kafka will push all those events to the consumer. In Kafka, we use the pull based approach, or the consumer will pull the events from Kafka. So even if the consumer is slow, it is totally fine. Consumer can consume the events by polling from Kafka at its own speed, because the events will stay in Kafka till the retention period, and retention period is enough, like 7 days or even 28 days, correct? So that is enough time. Even if your consumer is slow, it crashes sometimes, the Kafka provides durability. The events will stay in Kafka, and consumer can consume the events slowly using the offset, correct? So by the poll based approach, Kafka naturally supports Backpressure. So if the consumer is slow, it can poll less frequently, correct? So there is no problem. Problem would have happened if Kafka is pushing the events. Then consumer needs to consume those events, otherwise those events would be lost. But here we use the polling based approach. So that's why there is no issue even if the consumer is slow. And also, as we know that Kafka acts most of the time as a event stream, so there can be multiple consumers as well. So here I am treating these as different consumer groups. So both of these are, say, consuming from a partition. Okay, that is totally allowed. And even if one consumer is fast, other is slow, again it is totally fine, because these are independent of each other. Why? Because of offsets. Both of these will have different offset, because offset is unique per partition per consumer group, right? So these can operate independently. So that's the beauty of Kafka. Now there are other strategies as well that can be used to support even more Backpressure. Like consumer can poll lesser amount of events from Kafka because it is slow. And there can be many other things, but we don't need to discuss that. The important point is Kafka naturally is supporting the Backpressure because we are using pull based approach here. The next question is, what happens internally when a topic is created? So when a topic is created, Kafka controller comes into picture. So Kafka controller will create the metadata. Then it will assign the partitions to brokers, because as we know, for a topic, we will have multiple partitions. Right? So for example, we have three partitions, P0, P1 and P2, right? So there are three partitions. Now these will be assigned to different brokers, and also there will be replicas for each of these partition, correct? So we need to do the assignment to broker, and we also need to assign the leader from where the reads and writes will happen. So that work will be done by Kafka controller. Okay. So Kafka controller will create the metadata, assign partitions to brokers, and assign leaders and followers. Next, the created metadata will be stored in Kafka's metadata store. So earlier, Zookeeper was used for Kafka's metadata store, but now Kraft is used. Now after this, next question is also related to topic. The question is how to add a consumer group to existing topic. Like we mentioned, consumer will subscribe to the topic. So how will that happen? So this needs to be done. We assign the group ID as the consumer group name, okay, and say the topic is orders. So we will do consumer.subscribe orders. So consumer is part of this consumer group. So we have defined the consumer group, and then we do consumer.subscribe, and inside that we tell the topic name. Now why consumer group is required? Because as we discussed earlier, only one consumer from a consumer group can consume from a partition, right? So two consumers from the same consumer group cannot consume from the same partition, although they can consume from different partitions. So that's why we have mentioned the consumer group ID here, and then we did consumer.subscribe and pass the topic name. So after this is done, now it's the responsibility of Kafka to assign the partition to the consumer. So after this, the next question is, why is Kafka so good at handling massive writes, or how does Kafka handle huge number of writes? So we know whenever there are huge number of writes, we prefer Kafka. You might have heard saying me that in these system design videos as well. So you can refer to these videos to understand what is the role of Kafka. But coming to the question here, like we know Kafka is great at handling writes, but what is the reason for that? There are multiple reasons. So let's try to understand those one by one. Okay, the first reason is append only log. We know that Kafka is a distributed log file and we just perform the append operation at the end of the file. We do not perform update or delete operations in Kafka. So there are no random writes. We always append at the end, and there are sequential disk writes which are fast. After this, the second point is OS page cache. So Kafka relies on OS cache. So when the write operations happen, they hit the memory first and the disk flush happens asynchronously. Now because the other operation is happening asynchronously, you don't have to worry on the write operation. This OS page cache is also very helpful when we talk about the read operations. Okay, here we are talking about the massive writes. Similarly for massive reads also, this is really helpful. The next reason is batching. So producers send batches, not single messages. So we will have fewer calls, better compression and high throughput. The next reason is parallelism due to partitioning. So the write operations are spread across partitions, and due to partitions we have parallelism in Kafka, and that's why it's really scalable. So multiple reads and writes can happen from the partitions. And the fifth reason is Kafka does not perform any major operations on the events. What I mean is Kafka broker does not serialize message, does not apply any business logic, and does not filter per consumer. So it will simply append it, serve it and replicate it. So it does not perform any other things like deserialization or any other business logic or filtering. So it doesn't add any further cost on the write operation. Okay. So due to all of these reasons, Kafka is very good at handling the massive writes. Now this was about writes. Another question that comes into mind is, how does Kafka handle so many read operations? So the reasons are quite similar to what we discussed for the writes. It is able to handle massive reads because of sequential disk reads, it uses page cache, and there is no message deletion, and all the consumers read independently because of the offset. So even if 1000 consumers are reading the same data, we will have the disk read once and memory reads many times. You can understand like your actual storage is like the disk storage, like even in your laptop you have HDD or SSD, right? That is the disk storage, and then you also have cache storage. Okay, so the cache is much faster as compared to the disk because cache uses in-memory storage like RAM. Now when we talk about disk storage, we say like HDD or the SSD. Right now we know that SSD is much faster as compared to the HDD, but when we talk about cache, which is RAM, so RAM is much faster as compared to the SSD and HDD. So that's why it's like very fast also, and you don't need to hit the disk again and again. You can directly serve from the cache. So these are the fundamentals, like you can refer to these videos of mine and you will get more clarity. But I am just telling these fundamentals to tell like similar kind of concepts are also used in Kafka. Like it uses page cache. Okay, so the next question is, what is the difference between PubSub and Kafka? Okay, so let's try to understand this in a very simple way. First, as we know how Kafka works, so let me just give a brief summary of it. Okay, so let's say this is like producer, and then there is Kafka, right? And then there can be multiple consumers, correct? So there can be multiple producers and multiple consumers. Okay, so the producer will send the events to Kafka. Now the consumers poll from Kafka. The message is not pushed to the consumers. Consumers poll the messages. Okay. And one more important thing about Kafka is that the event stays in Kafka till the retention period. Okay, so say the retention period is like 28 days. So the event will stay in Kafka for 28 days. So Kafka provides durability. Next, if we talk about the ordering guarantee, ordering is not guaranteed across the partitions, but within a partition, ordering is guaranteed in Kafka. Now, similar to this, let's talk about PubSub. So in PubSub, you have publishers and subscribers. Okay, so I've mentioned here publisher. Okay, and then you have your PubSub model. So let me write here PS. Okay, and then you have subscribers. So the term that we give to the consumers in PubSub is subscribers. Okay, now there can be multiple publishers. They basically send the messages to PubSub model, and subscribers have subscribed to the topic, just like consumers subscribe to the topic in Kafka, subscribers subscribe to the topic in PubSub. Okay, the only difference is when PubSub gets the message, it will push that message to all the subscribers. So all the subscribers which have subscribed that topic, they will get the message via PubSub, because PubSub will push the message to all the subscribers. We know in Kafka we use polling. Okay, consumers poll the message, whereas in PubSub there is push based model. All the subscribers get the message, so message is pushed to the subscribers. And another point here is each of the subscriber gets its own copy. Okay, so all of the subscribers will get a different copy, whereas when we talk about Kafka, as a consumer simply poll the events from Kafka, so they don't get the separate copies. Here we use the concept of offset. Correct. So here they simply fetch the events using polling, but here we use the push based model in PubSub, and each of the subscribers gets its own copy. Okay, so another difference between Kafka and classic PubSub model is that in PubSub, message will stay only till the time it is not sent to the subscriber. Once the message is sent to the subscriber using push approach, the message will be removed from the PubSub. Whereas when we talk about Kafka, it will stay till the retention period. So there is high durability in Kafka. One more thing is, like, if PubSub tries to push the message to subscriber, and in case subscriber is not active at that time, there can be chances that message will be lost. It depends on your implementation, but in classic model it is dependent on PubSub, okay, and not the subscribers. Whereas when we talk about Kafka, it's all on the consumers, because consumers need to poll the event from Kafka, and event stays in Kafka for like few days, right? So even if the consumer is slow or down, it can pull the events when it is up again, right? But it is not the case for subscribers. So Kafka is much more durable, and there is an option of message replay in Kafka which is not present in PubSub. Now one of the examples of PubSub is Redis PubSub. Okay, now what I told about PubSub here is a classic PubSub model. Of course there can be different implementations because there are different varieties in PubSub, but overall this is the picture you can understand. So I hope you got some clarity here. Now let's see in summary what we talked about, like what are the difference between the PubSub and the Kafka. First, if we talk about in terms of delivery model, okay, the delivery model of PubSub is push based, whereas for Kafka it is pull based. Correct, the consumers pull the events from Kafka, whereas in PubSub the messages are pushed to the subscribers. Talking about the retry, it totally depends on the broker or the PubSub. Whereas when we talk about Kafka, retry is consumer driven because of the offsets, right? So even if the consumer is slow or down, consumer can consume the events later because the event stays in Kafka till the retention period. Whereas in PubSub, it's the responsibility of PubSub model or the brokers present inside the PubSub to push the message to the subscribers. Depending on what implementation we do, retry can happen through the broker or the PubSub. But in case we don't handle it, some of the messages can also be lost. Say for example, your broker tried to push the message to the subscriber, but subscriber was not active, so that message may be lost. Now when we talk about the backpressure, which means the consumers or the subscribers are slow, but the producers or the publishers are fast. So that situation is naturally handled in Kafka because event stays in Kafka and it's about the consumers to poll the messages. So slow consumer is totally fine, but it is hard in PubSub because the PubSub model will simply push the events to all the subscribers. So in case the subscriber is slow, it will cause issues. Next, when we talk in terms of message lifetime, in PubSub, the message retention is until the message is delivered, because it's a responsibility of PubSub to push the message to the subscribers. Once the message is pushed, it can be removed. Whereas in Kafka, it stays there based on the time and size of the retention period. So by default, the retention period in Kafka is around 7 days. So the event stays in Kafka for 7 days, right? And of course, if your retention period is even more, like 21 days, so it will stay in Kafka for that longer time. Next, if we talk about replay, it is possible in Kafka because of the retention period, but it is not possible in PubSub because once the message is delivered to the subscriber, that will be removed from the PubSub. Now, if we think about a case that a new subscriber was added or a new consumer was added. So in case of PubSub, the new subscriber will miss the data because that message would be already removed from PubSub. But when we talk about Kafka, the late joiner can replay the event because that would be present in Kafka, and there are offsets, right? Next, if we talk about like consumer independence or the role of broker in PubSub versus the Kafka. In PubSub, broker tracks the delivery. So there is huge responsibility on the brokers in PubSub because we are following push based approach. Whereas in Kafka, we have offset, and offset is unique per partition per consumer group. So it provides consumer independence. So all the consumers are fully independent. So the next point is fan out. In case of PubSub, now because you need to push the messages to each of the subscribers, so each of the subscribers get its own copy of the message. Okay, so the broker duplicates the messages because it needs to send or push each copy to each of the subscriber. So it is memory and network heavy. But when we talk about Kafka, only one copy is stored. Many consumers read the same data, and that is possible due to the offset, and there is zero duplication. So when we talk about scalability in Kafka, it is very high. So we don't need to create duplicate copies here. Hence, this process of read operations is quite cheap in Kafka. Okay, next, if we talk about ordering guarantee, in PubSub, ordering is not guaranteed. But when we talk about Kafka, the ordering is guaranteed per partition. We don't maintain the ordering across partitions in Kafka, and that is for scalability. Okay, last but not the least, let's also talk about the throughput. Now, Kafka is very fast because as we discussed about the reasons like sequential disk writes, OS page cache, zero copy, batching, and there is no requirement per message acknowledgement to multiple consumers. Okay, but when we talk about PubSub system, it will do per message routing, it will maintain the subscriber list, and it will push the data eagerly. So throughput is not that high in PubSub. So overall, you can clearly see there are huge benefits of Kafka. So Kafka is not just PubSub, it is much more. And that's why using Kafka is an important component while designing big systems. Now, as I said, like Kafka is much more than PubSub. So again, a question may come like, why Kafka is not just PubSub? So because of all the reasons that we discussed here, like we can clearly see Kafka is much more than just PubSub, right? So in Kafka, we use pull based approach. So it's not the responsibility of broker to track per consumer delivery. And then we also keep the events in Kafka till the retention period. So that adds the durability. In Kafka, consumers are responsible for the state, and due to the offsets, all the consumers are independent of each other. And overall also we saw that the throughput is very high in Kafka. So basically, in short, if we have to say, Kafka is closer to a distributed commit log plus a PubSub semantics. So of course you can say like PubSub and Kafka are close, but Kafka has much more and better features as compared to the PubSub. Okay. Now the next question is when to use Kafka and when to use PubSub. So use PubSub when we have simple notifications. We have low latency push because we use the push based model in PubSub. So we need low latency push, right? And there is no need of replay because we don't store the messages after pushing it to the subscribers. And there are few consumers because if you are pushing the messages and if the consumers or the subscribers are too many, then it's like difficult for the complete system. It's difficult to scale as well. So in these cases, you can use PubSub. Now coming to the Kafka, you can use Kafka for more complex systems. Okay, you can simply imagine when there are a lot of write operations happening. Okay, so you cannot insert all the writes in database one by one. Okay, that is not scalable. So one of the scenario is like if you have huge amount of writes happening, you can use Kafka, because Kafka takes the events, and then after that there can be a microservice which can fetch the events in batch from the Kafka and then just make one write operation in the database, as it is putting all the data in database in one batch. So there is only one write operation happening for that complete batch of data. Okay, and then another scenario is like, say you have multiple consumers. Okay, now what does that mean? Say if we are talking about like designing YouTube, as I discussed earlier, or designing WhatsApp, you can refer to these videos where I have used Kafka, correct? So there are multiple microservices which want to perform something after something has happened. Okay, so there are multiple consumers here, or different microservices acting as a consumer. So in that case you can use Kafka. So whenever there is an event like video uploaded, okay, so all of these consumers will basically keep on polling, and once they get the message from the Kafka, they can perform their operation. Like after video uploading, you need to perform the transcoding, you need to perform the copyright checks, you need to do the analytics and much more. Correct? Now because there are multiple consumers, Kafka is good here, and we do not want to use PubSub here because we don't want to make a push based approach here, because then we are putting pressure on system, because these are different microservices. We want that they can operate independently, so they can poll from Kafka based on their speed. And also it's important to use Kafka in such complex systems because we want durability, right? As I mentioned, we are not inserting all the data in database one by one, right? And that's why we are using Kafka. And but when we do that, we want durability factor. If we simply use PubSub there, then that is not durable. In case one of the consumer is not able to consume that, if we have not done a specific implementation for that, there can be a scenario that particular message will be lost. And that is not good, correct? Because we have not also inserted in database. So we want durability, and Kafka provides that. How? Using the retention period, correct? So we can replay the messages and consumers can consume based on their pace. So in microservice integration, you will see use of Kafka. When there is high throughput, then Kafka would be required. And when there are multiple independent consumers, Kafka would be required. Okay. Again, you can refer to these videos. After watching this complete video, you know the basics of Kafka. When you see in the scenarios where I've used Kafka, it will give you even more clarity. Okay, so the next question is, what is the difference between Kafka and RabbitMQ? So in the beginning, I mentioned like Kafka acts as event stream most of the times, and RabbitMQ is an example of message queue. So basically we are talking about difference between the event stream versus the message queue. Both of these are really famous. So it's good if you get the clarity, like what's the difference. So let me try to explain you in a very simple way. As we know about Kafka, right? So we have producer here, we have the Kafka here, correct? And there can be multiple consumers, right? So the good part of Kafka is there can be multiple consumers. Of course, there can be multiple producers as well, but what we put inside Kafka is event, okay? Because events are immutable, correct? Because in Kafka, we don't perform like update or delete operation. So that's why we use events for Kafka. And then there are multiple consumers. And how do consumers get the message? They poll from Kafka, correct? So we use polling in Kafka, that we already discussed, and there is retention period in Kafka. So Kafka provides you durability. Now let's talk about the message queue or RabbitMQ here, correct? So say this is the message queue, or you can also say like task queue, okay? Or because we are talking about RabbitMQ, I'm just writing here RMQ, okay? The classic way of message queue is that you put task or message in it. Whatever you want to perform, that comes into message queue. Okay. So in Kafka, we had events, but in message queue or RabbitMQ, we put task. Okay. So there will be producer. And another important point for message queue is that for each of the tasks, there can be only one consumer. So in Kafka or in the event stream, we had multiple consumers, correct? So I have also mentioned here now Kafka mostly acts as event stream. RabbitMQ, it acts as message queue or task queue. Correct. So basically one important difference is like in Kafka, you can have multiple consumers for an event. Correct. Whereas when we talk about message queue or task queue, for every message or task, there can be only one consumer. You cannot have multiple consumers here. Okay, so you can clearly see a big difference. First clear difference is like you store events in Kafka, whereas in message queue, you store message or task, whatever needs to be done. And then talking about the consumers, for an event there can be multiple consumers in Kafka, but in message queue or task queue there can be only one consumer per message or task. Now another difference between Kafka and RabbitMQ is like in Kafka the consumers get the event using polling. So we use pull based approach, whereas in RabbitMQ we use push based approach. So basically it's a responsibility of brokers in message MQ or task MQ to deliver the message to the consumer by push based approach. Another difference is like in Kafka you have retention period which provides durability, which means like if the retention period is like 7 days, so an event will stay in Kafka for 7 days irrespective of the fact like if all of the consumers have consumed the event or not. Okay, but when we talk about RabbitMQ, once the task has been consumed by the consumer, it will be removed from RabbitMQ. So in Kafka you get an option for replay, but you don't get that option in RabbitMQ. And another point is because in RabbitMQ we are again using push based approach, so consumer state is maintained by the broker in the RabbitMQ. So it becomes the responsibility of the broker of RabbitMQ to deliver the message to maintain the state of the consumer. Whereas in Kafka, because consumers are doing polling, so it's a consumer responsibility. It's not the responsibility of Kafka's broker, because consumers simply can use the offset from the internal topic of Kafka, and based on that they can poll, and all the consumers are independent of each other because of offset. Now of course RabbitMQ is also very famous and it provides some of the features, but here I'm not talking in detail or going in depth for RabbitMQ. My main focus was to tell you the difference between event stream versus message queue. Okay, so RabbitMQ also has few of the features, because I am telling in generic about message queue, but when you talk about specific task queues, they have their some specific functionality which is very useful in some scenarios. But here the overall we are talking about event stream versus message queue. Okay, so in summary, if I have to tell in tabular or text form like what is the difference between Kafka and RabbitMQ, then it would be something like this. First of all, in Kafka we store the events, in RabbitMQ we store the task or message. Okay, so Kafka is event log or used as event stream, whereas RabbitMQ is used as message broker or message queue or task queue. Now in Kafka we use pull based approach, that is the consumers pull events from the Kafka, whereas in RabbitMQ it's a push based approach. In PubSub also we had push based approach. One more important difference is in Kafka you can have multiple consumers for an event, but when we talk about the message queue, in that you can have only one consumer for a message or task. So this way the message queue is also different from PubSub model. In PubSub model we had multiple subscribers just like the event stream Kafka, correct? But in message queue we have only one consumer. Only one similarity between the message queue and PubSub is that both use push based approach. Okay, coming back to this one only. Like when we talk about replay, it is possible in Kafka, but it is not possible in RabbitMQ. Talking about the retention, Kafka, as we already know, time-based and size-based retention is there, so it provides more durability. For RabbitMQ, it is the message is present until it is acknowledged by the consumer. Once we have already delivered the message or task to the consumer, then it will be removed from RabbitMQ. So when we talk about consumer state, in Kafka it is the responsibility of consumer, whereas in RabbitMQ it's the responsibility of the broker of RabbitMQ, correct? So in a lot of places you would see we would use like Kafka as an event stream instead of the message queue. Now because we are talking about message queue, I remember that in the beginning of video we were in a question like, is Kafka message queue or event stream? And I just gave you the brief and I said like, let's cover the topics first and then it will be easier for you to understand, right? So now it's a time to discuss this question. Okay, as I told earlier, I thought for a long time that Kafka is a message queue. Okay, but actually, most of the time, Kafka acts as event stream. Okay, why? Because we already know that in event stream there can be multiple consumers for an event, right? And Kafka provides that functionality, so there can be multiple microservices which are consuming the same event, right? So that's why most of the time it acts as event stream, and that is why it is so powerful. But there is also a scenario in which Kafka acts as a message queue as well. How? Let's talk about it. So say this is the partition, okay, partition 0, okay, and this is consumer 1, this is consumer 2, and this is consumer 3, correct? Now say these are part of different consumer groups. Okay, this is CG1, this is CG2, and this is CG3, right? So we have different consumer groups, and inside that we have the consumer, correct? So it is totally fine if this consumer C1 consume events from partition 0, similarly consumer 2 and consumer 3. This is totally fine and this is acceptable, and that's the functionality of basically Kafka. And in this case, Kafka is acting as event stream, correct? Because multiple consumers consuming. Now let me remove this basically. So I've removed that different consumers. Now just imagine like these are part of one consumer group, okay, and this complete is a one consumer group. Let's name it as like CG1, okay. So CG1 is a consumer group in which we have three consumers, C1, C2, C3. Now as a rule that we already know, multiple consumers of a consumer group cannot consume events from same partition, right? So if C1 is consuming events from P0, C2 cannot, right? Only one consumer per consumer group can consume events from partition. So in this way, if you see this kind of picture, there is only one consumer allowed, right? So if there is a scenario that you have like only one consumer, or you simply think of one consumer group, even though it can have multiple consumers inside, but only one of those is allowed to consume the event, then in this case you can think of in a brief kind of scenario that Kafka is acting as a message queue because there is only one consumer. But again, it's just a kind of thinking that you can make, that Kafka can also act as a message queue. Most of the time, the majority work that Kafka performs is event stream, and that's the main power of Kafka, correct? We saw like differences between RabbitMQ, and we saw that most of the times what we want is like Kafka to act as event stream, right? So that's why the power of Kafka comes as event stream, and mostly it acts as event stream only. This is just kind of a, you can say, one way you can think of, like, okay, it can also sometimes act as message queue, but overall if we talk normally, if someone asks you, Kafka is actually an event stream, right? So this is just kind of theoretical kind of thing, but normally Kafka is event stream. Okay, all right, now let's move to the next question, and the next question is, can a partition contain event of multiple topics? We saw like a topic can contain multiple partitions, right? But can a partition contain events of different topics? The answer is no. A partition belongs to exactly one topic. So for example, if you see here, we have topic A. Inside that we have like this partition A P0 and then A P1. So this topic has two partitions. And then topic B, again it has two partitions, B P0 and B P1. So clearly you can see the A P0 and A P1 will contain all the events related to topic A only. And similarly, these partitions will only contain events related to topic B. So there is no mixing and no sharing, which makes complete sense. Do you remember the first example I gave you related to the sports? Like we created first topic as like football events, right? And then we created like cricket events. Now we have partitions for the topic. So say for example, for cricket, we have like three partitions, P0, P1 and P2, right? So we have these three partitions. So this makes complete sense that these partitions should contain the events only related to cricket. In case they take events for football as well, it will become a complete mess, right? So here it is like these partitions are handling the cricket related events only for different matches. correct? So that's why a partition will only contain events related to exactly one topic. Okay, and we saw earlier in this video as well, when you create a topic you need to mention the partition, correct? So partitions are specific to a topic. It's just like topic is logical whereas partition is physical. Now because we are talking about it, so next question is also similar to this one. The question is, do we create new partitions for every new topic? The answer is yes. It is related to above question. As we saw, like partitions are never shared. Okay, they have events related to exactly one topic. So whenever you create a topic, you also define number of partitions, right? So yes, new partitions are created for every new topic. So basically when you create a topic, so for example we are talking about topic orders, and we provide number of partitions in it. So here it says partition 6, correct? Now corresponding to this, the Kafka will create these 6 partitions. Okay, you can see the topic and then the partition number. So these partitions are independent, mapped to brokers, and stored as separate logs on disk. So in short, the answer to this question is yes. Now because we are talking about partition, let's also see how data actually looks like in Kafka. So if you see here, this is kind of like how physical data would look on the broker disk. So this is the broker. Inside this you can see different partitions present, like orders 0 is there, orders 1 is there, payment 0 is there, payments 1 is there. So different partitions are present, and they are also representing the topic first and then the ID of the partition. Now because as we discussed earlier in this video, a broker can contain different partitions covering different topics, correct? For example, this is covering orders topic and this is the partition related to payments topic. So different topics, and it is totally fine because broker is similar to the stadium in the sports example, and in same stadium you can play different sports, correct? So you can also have football match and cricket match in a stadium on different days, right? So in similar terms, the broker can contain partitions of different topics, correct? And inside this partition we can see we have the log file and the index. So this is how the data looks like inside the broker disk. But the main point is orders 0 partition will contain events only related to orders topic, and similarly this one, when we talk about these two, these will contain the events related only to payments topic, correct? And the partitions are independent of each other. Now let's go to the next question, and the question is, can a consumer in consumer group consume from multiple topics? The answer is yes. So say we have this topic like football events, correct? And then we have another topic related to cricket events, and we have one more related to tennis events. Okay, so there is this consumer inside a consumer group. So consumer group is CG1, consumer is C1. So yeah, it is totally fine. It can subscribe to football events, it can also subscribe to cricket events, and it can also subscribe to tennis events. So that's the beauty of Kafka. So a consumer can subscribe to multiple topics or even a regex pattern. Like you can also do something like this. Okay, of course using this you will subscribe to many topics where you have like anything replaced by star here, and then you have the event. So maybe you, if you want to subscribe to all the topics, you can also do something like this. And then once you subscribe, Kafka will assign the consumer partitions across these topics. Now this was related to multiple topics, like consumer consuming from football events, cricket events, tennis events. So these were different topics. Next question comes is like, can a consumer in a consumer group consume from multiple partitions of the same topic? So now we are thinking in terms of same topic. So let's say we have like partitions P0 and we have like P1 and like P2. Okay, so we have 3 partitions. Now all of these partitions are part of same topic. So let's say the topic is tennis events. Okay, so it contains the events related to tennis, and of course there can be multiple partitions in the topic. So we have these 3 partitions related to this tennis event, and of course these might be present in different brokers, right, to avoid single point of failure. Now our question was like, say we have consumer C1, okay, and this is part of some consumer group CG1. Okay, now can this consumer consume events from multiple partitions of the same topic? So the topic is tennis events, and inside this we have these partitions. So is it possible that C1 consumes events from partition 0, P1, and P2 as well? The answer is yes, it is completely fine. The only restriction is that because now C1 is consuming events from say partition 0, any other consumer which is part of CG1 same consumer group should not consume from the same partition. That's the only thing. So for same partition, only one consumer per consumer group. But overall, one consumer can consume from multiple partition across different topics as well, and across different partitions in the same topic as well. And this situation is very common when we use Kafka. Say you have lesser number of consumers as compared to the partitions, which is very common, right? Because your consumer groups will be like the microservices, and you will have limited microservices in your complete system, but there can be so many partitions. So you may have like limited number of consumers but many partitions. So it is totally fine that a consumer is consuming from multiple partitions, whether it can be related to different topics and even to the same topic. So for example, if you see here, topic has 6 partitions and the consumer group has 2 consumers. So C1 and C2. So C1 is consuming from partition P0, P1 and P2, and C2 is consuming from P3, P4, P5. All of these partitions are part of same topic, correct? And a consumer can consume from multiple partitions from the same topic. Alright, with this we have reached to the end of video. We discussed a lot about Kafka, okay, the internal functionality, how things work. Now of course you don't need to remember all of these concepts. You can revise some of the concepts and that will be helpful for you in understanding overall about Kafka. What you can do is like revisit this video again after some time, so that you can keep on revising the stuff. Okay, and basically in this video we have checked about Kafka, like how things work in Kafka, but we also need to see like how do we use Kafka in designing complex systems. So I have couple of videos here related to YouTube and WhatsApp in which we have used Kafka while designing the system. So you can refer to these videos and you will see, okay, this is how whatever we studied can be used. Okay, so if you found this video helpful, press the like button, subscribe to the channel and share it with your friends and family so that all of us can learn and grow together. Alright then, this is Mohit Chabda signing off. Subscribe to the channel and thanks for watching.